Well,
I guess I heard a version of this talk at MIT a couple years ago.
yeah,
Wow.
I read about that. Made the news. This is entirely different.
Oh, okay. Even better. What do you think about one-bit floats?
I'm getting close. I'm getting close. It's 10. Should we start?
Like, those of us that can always watch the videos.
One more. Well, hello and welcome. I'm Jeffrey Sarnoff, and I'm here to talk about fast floats for deep learning. The IEEE has a working group charged with developing small format floats for this purpose, and I am honored to be editor-in-chief. I'm going to discuss these families, the nature of the floats themselves. This is not a talk about how to use them. It's a talk about how they come to be made numeric. So the first thing that we did is the top part, the signed, and then eventually it occurred to us that for block floating point operations where you have a block of numbers and they're all scaled by the same single value, unsigned was very helpful and appropriate. There are 4 families, and 2 are signed, 2 are unsigned. All of the families have a single NAN, and the families are split between the finite and extended versions, the extended versions having support for infinity. I took the work of the committee, which is still not, it's not a standard. It's not a standard until the IEEE says it's a standard, so everything I say, take it with a grain of salt, although we've been at this for a couple of years now. So I wrote software to model and test and make sure that what we were doing from the perspective of a software architect was reasonable and better than reasonable, made life easier, and had no hidden problems. That was a repeated effort because it's a standard in development, things change. But we do have these families, and there is a way they are named. It comports with IEEE 754, which is the long-time standard for floating point arithmetic. Starts the word binary, then you have the number of bits, followed by P for precision, the number of bits of precision, and as you see up on over there, the suffixes to determine which family you're dealing with. Now, a lot of this is my own artifice, but fairly reflects what's known about the work of the committee. All right, so these are not your ordinary familiar floats. There are some major differences. One is we have only 1 0, there's no negative 0, and we have only 1 NAN. There are not many NANs because, well, part of it's stylistic and part of it is there are just fewer code points to deal with, so one has to be careful about how they're used. Another big change is we've ruled out having exceptions. So this is because of the nature of the workflow in deep learning. You have massive amounts of work and resources taking a lot of time, days, weeks, months, and you just can't be in the business of interrupting what you're doing because of some exception, trying to deal with it and coming back. It just slows everything down tremendously, and it makes thinking about how to do it much harder. So we got rid of them. Now, implementations are allowed to provide their own additions, whatever, but they can't use the names that are used in the standard, and they have to specify exactly what it is they're doing. The abstraction hierarchy, and I lean a lot on the abstract. I'm going to be revisiting this. The abstraction hierarchy follows directly from the diagram of the families, and the names accordingly. The AKO names, the AKO is for a kind of, and those are my leaf abstractions. The structs themselves use those leaf abstractions as their superclass. What is so very nice about using the abstractions is being able to compute over them, because generally it's a simpler approach, fewer headaches when you can do it and it works. In this case, all of the abstractions that for these families carry as parameters bits and the precision. And it turns out that that's really enough, well, certainly enough to derive other critical descriptors of a member of one of the families, and it's enough to get a great deal of the work done. Some simple examples are, you can certainly figure out how many values you've got, how many fractional bits, and the last one, the bits in the exponent, it has the term is unsigned, because for unsigned floats you don't need the sign bit. That sign bit gets put into the exponent for additional dynamic range. So from any abstract leaf, we can construct the float per se. And I use AI float as our generic interface. With the abstractions, you just put in the leaf abstraction and you will get back the encoding and the float values that match to each encoded value. You can do the same thing concretely using the essential parts of the float that you're intending, giving the bit width and the precision, and then whether it's signed or unsigned, and whether or not it's finite or extended, and you get the same thing. Well, that's interesting. Here we go, do it the old-fashioned way. So what I found in going through this, and it's not, it presents as not a lot of work. In fact, it was 6 full revisions before I got to where I really was comfortable with it. And one of the things I found is that this mixing of abstract and concrete in a way that you didn't have to think about it, because if it worked one way, it works the other, was really opening for a lot of possibilities. Here, the AI with a little soccer ball just stands for abstract AI float, because it doesn't fit to put it all in. And it is true that anything that can be addressed, given a concretized or realized version of one of the entries in a family, can be done abstractly, and vice versa. And this is where things really start to shine here, because after writing up the logic for the abstractions, to get it to work with the actuals, the realizations, this is all that's required. And it's just the 3 lines of code. And it works. Families have invariance things that are true regardless of whether you're talking about a 3-bit float or a 15-bit float. Let me take a moment to expound on that. We're covering floats where the total bit width is as small as 3 bits to as wide as 15 bits. 16 bits and above is currently with the other standards group. And for those, you can have all of the precisions that are available, you can use. For signed types, the precision ends up, you can't have the precision be the same as the bit width because odd things happen mathematically, but you can for unsigned. So there are a lot of things to choose from. And one chooses, presumably, to maximize the effectiveness in whatever application is involved. A conforming implementation does not need to provide all of those floats. It can provide as few as one of them. Will tend to provide more than one, but there's really no expectation that everybody is going to spend transistor resources to make sure all of the possibilities are available. It will be target dependent. So we can go from the number of magnitudes, which is, magnitude is essentially the absolute value, and using that, that turns out to be very handy in figuring out other things. And it's up here on the screen so that I can point out the kind of symmetry of a sort between the unsigned and signed here, where in each case you take the number of values and you do something involving 1 with it. In one case you subtract the 1, in the other case you shift down by 1, but it's shifting is essentially multiplication, right? So you have the two kinds of basic arithmetic operations shown in the world of the unsigns and the world of the signs. Similarly, if you want to know what code point your NaN is at, you can find that out, or your 1, you can find that out. There's a fair amount of discussion about the utility or disutility of subnormal values. These are tiny numbers, and some people argue that, well, there's overhead and they're slow and I don't really need them, and they quash them to 0. And other people feel differently. It used to be the case that subnormals did take more time. That hardware manufacturers have gotten very good at that now, and there's really not much cost to it. They're also, well, which side do you want to go down, right? There's subnormals are smoother. Your gradient stuff is more nicely behaved. Sliding down the rocks is not so good. And just a point of art, subnormal 0 is not considered a subnormal. When you take the count of the number of values that are subnormal, because 0 isn't in there, it throws off a lot of other stuff down the line. So I've coined, and please promulgate the term prenormal to include 0 with the subnormals. It makes a lot of the computing that takes that into account easier. You do want to be able to quickly identify where do my normal numbers start, where do they end. Infinity is also not a normal. And it, pardon? Is it post-normal? You bet. You bet. So we can find that out. You want to know in lots of kinds of analyses whether you're dealing with a normal value or not, and by looking at the code point, the code points directly encode the values. The way I'm talking about is the values are a separate group of, piece of an array or something, but it certainly is not, doesn't have to be that way, and often isn't, because when you're working with the code points, the directly encoded values, you can do some pretty amazing stuff. You can take the most complicated, highly graduate level, PhD level, univariate expression you like, right? And you can put all of the answers into a small table because these are small numbers of values for each kind. So that you can then cascade transformations just by going from one piece of a small table to the next, like daisy chaining the direct encodings. And that's a big deal. All right. We have, this will be, when it's approved, it will be the first standard, international, well, national or international standard, that has formal verification with it at its introduction. This is very comforting. Linus will tell you. It means that you don't have to be concerned about watching out for NANDs when they may occur, when they pop up, because they'll only arise where they're specified to occur, and they cannot arise anywhere, and that's been formally verified. We have the proof. Similarly with infinities, and a sequelae is that the floating point operations themselves will comport with their specifications. They're not going to go, there are not uncovered edge cases, as it were. So that means that when using this formulation, you can take it easier. There's not bad stuff that you have to worry about that you don't bring to, unless you bring it to this. A brief look at the specification. It's not really, the details are not important. What's important is that all of the things that are specified, the parameters are listed, the operands, the output, and its behavior is characterized. And also, here's addition. I'm not going to go into the details. What is of note here is if you look up at the signature, you see the FX, FY, and FZ. Those are, it means that each input can be of its own format. Again, we don't require that a conforming implementation support all possible combinations. They can, pick one or two. That's perfectly fine. But the specification itself covers all combinations. And the last item of note is the pi symbol used for projection. Projection means it combines both rounding and it combines capping, as it were, getting rid of the infinities, closing the domain to infinity, so that you're in deep learning, you don't, there are many times where an infinity showing up is not going to be helpful, and it's much easier to have the computation roll on if you're dealing with normal values. So we roll those into one. And more details. We have two groups, larger groups of numbers. The extended reals is something that's been used a lot. It's the real numbers plus infinity. We introduced the augmented reals, which is that and nan again attached. It turns out that particularly in proving things, it becomes simpler to use the augmented reals. I'm sure this is a familiar picture. And the point is just to reorient one's thought to the bit fields, because we're going to go into that. On the top are the role of the exponent, on the bottom the role of the significand, and just note that the first two rectangles have the same outer color, and that the second, third, and fourth squares do. Because I think of them as spans and cycles. The exponents span each cycle. The cycle incorporates all possible fractional bit patterns. Here it's shown with 2, but there could be as many as there are significant bits. And the span, the exponent, here you see them valued as if it were the raw bit field, and then subtracting the bias so that this allows exponents to be both positive and negative, which is useful because you want to be able to grow and shrink things. The only unusual part here is these little steps that take the -1 and put it on top of the -2. That's because this first column is for the subnormals, and for technical reasons, the subnormals need to have the same exponent as the initial normals. These things, the bias brings things more into balance, and exponents are computed as by taking 2 to the number that is the exponent with the cycles are the fractional bits, and here you see the broken into subnormals and normals. The subnormals, you get no implicit bit added to them. The normals get a 1 added to them. And you see on the bottom row the significand values that result. Then to actually get the value, the binary rational that you're going to compute with, you multiply the exponent and the significand, and the lower row gives you that. You see that at the very end, nan is overtaking the last position because all of our representations have a nan, and this is unsigned, so nan goes at the end. For signed, it's between the positives and the negatives. And let me close with this. I've been using Julia for a very long time, long before anybody ever thought there would be a version 0. This, it's been quite helpful to me. I threw away all my other programming languages. I thought about what I had come to learn about how best to work with Julia and how best to have Julia, let Julia work with me. This is the result of 14 years of experience with Julia, and here we are at JuliaCon. Please take it as my best information. Thank you.
Covering for the chair of this session, and thanks for the fascinating talk. Any questions for Jeff? We have plenty of time.
All right. Yeah, Alan.
Are there any existing? I kind of like the method where the person on the at the podium just repeats the question, but you always have to remind them.
Thank you.
Because nobody ever remembers to repeat the question. So I'm just wondering if there are any existing formats made by any chips that don't fit into your
Well,
standard.
so the question is, are there any existing formats made by current manufacturers that differ from this? And the answer is all of them, right? Because this IEEE standards drafting group, came to be after a bunch of those things were around, and we are specifically charged with not feeling overly bound by what's there. Our charge, we have representatives from industry and academia and people like me. We have worked very hard to do the best for the future user of the standard and not be too worried about the present stuff. Now, there are people on the group who have a lot of experience with this, and well, if you're doing some of what's out there now, doing this is not such a stretch, but no, there is no like this now. Yep.
Thanks for the interesting talk.
Yeah.
So if I understood correctly, then quantization will be almost trivial in this setup.
Well, you won't have to worry about it, but certainly an implementer will have to. It happens the math is happening in a math place, and it's being projected into the format of your choosing, and that's done given whatever rounding and saturation kind of setting that you want to apply. So that's all that the client need to be concerned with, and yeah, it'll all work. The implementer has to make sure that it work right.
But the computation will only happen on the data type level, right? So if I
Yes,
train something
The
with
question, the question is, so the computation basically happens on the data type, and the answer is yes. And in large part, and wherever possible, we have sought to simplify things.
As kind of a follow-up to the first question, when do you want to when do you think, or do you think that the industry standard will become the same as the IEEE that you just presented?
I can speak from history. 754 was in much the same position. There were lots of competing versions of how to do floating point arithmetic and what floating point values were. And there was, you can look at the records, there was a lot of concern about, will industry adopt that? Well, it did. And, you know, industry will do as it feels is best for it. However, I would not have put in the time that I have put in and the focus that I have given this if I thought that it would not be, there would be no fruition.
Do you have a modern day Kahan to beat everyone under the table?
I have better than that. I have,
I want to repeat the question.
I don't know how to repeat it. Loosely, it was, do I have a subtle way of influencing industry to adopt this? And the answer is, I don't, but their clients do. And clients, big clients, say, I need something that comports with the standard because that's what my customers demand. And this is going to be it. A client who wants two vendors can have two vendors. A client who wants to develop their own chips can develop their own chips. This isn't proscriptive, it's prescriptive.
Yeah, we still have a few minutes for more questions. If we have, please.
Just very quickly, what were the languages you threw away?
Oh, that's a great question. So, I once wrote a resume that listed all of the languages with which I had had experience, and I was able to do one for every letter of the alphabet. So many, many. Julia really gives me a sense of comfortableness in the using that I remember this from one of the first JuliaCons. We were asking people, what made you come to Julia? And everybody's answer was, I'm just so tired of the tears that came with using, you know, massive C++ or Fortran projects. And it is a world of difference. Yeah, that's my answer.
All right, let's thank Jeffrey again.
Thank you. Give me a moment just to move this stuff off. That's the HDMI.
Is there a USB-C adapter? I thought they were announced to be in every room.
So
Yeah. Yeah. Sasha, plug in.
All right.
Um,
Right. Our next talk is from Sasha Palavin about accessing the JL beyond at set or a tour of the optic land. Please take it away.
Yeah, thanks everyone for coming. And accessors.gl is quite a popular package. You might have seen at set macro in other packages, in end user code elsewhere. But even though it's a popular package, I would say that it still has some features that, in my opinion, are underused. And I will talk about them and the overall design and what it is, really. So just to clarify, it's not optics in the physical sense. So it's not like we take a beam of light, do something with it. It's not this kind of optics. But optics is just kind of term in programming for functional references. I won't assume the knowledge of like either optics or accessors.gl in my talk. I will give like intro as well. And the plan of our tour will be like what is it, why it was accessors.gl was introduced, how it works roughly. I will overview a few kind of nice, common and neat use cases and discuss some design questions as well. So this is the accessors.gl package. It is, so the very kind of basic APIs that you might have seen being used is kind of just operating with immutable structures as if they were mutable. So, of course, you cannot do kind of name tuple dot some field equals something, but you can make a copy in a convenient way using set macro. It looks almost exactly the same as working with mutable structs, but it creates a copy. So accessors.gl, it's pretty old. I mean, it's been developed for many years, and the original main author is, and he's still active, JW3126, and since about 2022, I've been doing a lot of bug fixes and new features and cleanup as well. So, first of all, how it works. Of course, there is no magic. I think I'll try actually. Oh, I guess it's kind of stuck here. So there is no magic. When you see at set and some property setting, it just expands to regular Julia code. Everything is kind of clear and can be explored with macro expand. And the property lens implementation is also pretty short. It just gets get property and calls set properties on set. So from just this example, I would say it's not really clear why would you use accessors at all if you have these nice functions like get property, set property. So there are a few key features, and they really kind of circle around all kinds of like composability. So accessors is generic. The idea is that set function and set macro, they aim to support all functions, not just property access. Wherever it makes sense, you can make like set first element in our array equals 100, and it returns you a copy of the array with this modification done. You can set a year of a date or like a lot of other stuff. The idea is that it should work for any function where it kind of intuitively makes sense. And what accessors brings you is, in addition to supporting a lot of these functions by default, is also composed functions are supported. So you can have an object with nested fields and nested arrays, nested elements, and modify something very deep within this object and return a copy of everything. So this makes operating with immutable structs very convenient, and they are still performant. And in addition to, of course, the set macro may provide a convenience interface. Instead of writing these composed functions just by yourself, I would say this is as convenient as it can in principle get. You just set whatever function, like arbitrary function you have of your object, and it returns you a copy. So this is the basic kind of promise and aim of accessors. It has more stuff, more involved stuff that maybe you want to modify several objects at a time, maybe you want to insert, delete. I would say, so I won't stop much on kind of parallels to other languages, but I think in Julia, at least for me, it was kind of the only language where I found it like really useful in day-to-day work. Yeah, and there is even more. So as I said, there is like not just set, but modify, insert, delete, get all, set all for multiple values. I have an accessors extra package. From time to time, something is upstreamed from there if it is generally useful and can be implemented cleanly, but kind of not everything that is useful is upstreamed yet. So then I guess to the kind of nice part, probably more, and the kind of part that doesn't require any understanding in advance is that what would you use it for? So I would say that I personally use accessors for like for everything really. So the base idea is that if you want an object just like the object you have with just some arbitrary function, nested, simple, complex, anywhere, it doesn't matter, change to a new value. That's just add set to a new val. And there are just kind of some examples. Maybe you want to if you have all the structs that are immutable, or you don't want like race conditions, so you can just change nested properties. You can change like nested arrays, nested objects in any way. I would say this is kind of just how you would intuitively think about modifying an immutable structs. You want the same object, just with something inside it changed. It can be property or a function. More advanced stuff includes recursive optics and manipulating, for example, all objects of some type within your structure. So, for example, if you have your object where you have different geometry primitives, some of them are polygons, you can triangulate all of them at once, and you will get back the same kind of object with all polygons replaced with their like triangulate calls. So if you have a JSON object and you want to convert everything to dictionaries, not dicts, you can do it the same way. You can just select all the recursively select all JSON objects and apply the dictionary constructor to them. It just works. It's convenient to work with expressions because they are fundamentally nested objects. So here you can define, okay, like I want to select all sub-expressions that kind of follow this condition and extract them. So all kinds of this work. Another kind of use cases is really using and defining the API of your packages using the set function. So it is generally common, not just in Julia, to have some function and being able to get and set this function of an object. And very often, I mean, not extremely often, but from time to time, I see it being defined as like f and set f. To kind of save the user from learning different functions like f and set f separately, consider defining f and the accessor's set function with it. There are some examples in the ecosystem, like in the interval sets. Maybe you want to modify the left endpoint of an interval, set it to some value, and return another interval. That's really the API for that. In some kind of numbers with uncertainties, you want to modify the value or uncertainty. That's also how you can get it with set. In axis keys, you have your regular keyed array. Want to modify axis keys for some axis and return the resulting, like the new array back. That's how you get it. So I would say that it just makes sense as the API for a package if you consider having these two functions for immutable structs. Just replace the set f with the accessor set function. Regarding more kind of specific use cases, neat one is you can have mapped arrays with automatic support for modification, for set index, for push. There is a map view so you just pass, instead of just a lambda function, you pass an optic here that selects the A property times 10, and you can set, if you do set index on this array, it modifies the original array because it knows what is selected in Y and how to get back from Y values to X. I think this is kind of the cleanest way to get automatic modification on a mapped array. You can use it in differentiation. Everything in accessors is type stable, performant, and like a lot of effort is paid to that. So the top line is just the definition how you like. This is really the implementation. If you want to find the derivative of some arbitrary function, taking an arbitrary object at some value of its object, and this is a usage example. So this is a function that just your regular Julia function. The next line is what is the input object you want to differentiate in, and the third line is with respect to what part of this object you want to differentiate. The same, of course, works with gradients, and yeah, with any kind of structs, accessors, and packages it's built on. They pay also a lot of attention to be as generic as possible. Another neat use case is, so let's say you just define your kind of model or a struct that you can evaluate. Here it's just your regular Julia code, no accessor stuff whatsoever. And if you define what properties of your functions, like they can be nested, there can be multiple of them. If you can define like what properties you want to adjust, then there is just a small convenience function that gives you this whole UI with all the sliders and stuff. And this is really built on being able to get and set the values specified by optics. So it does work. I use it just kind of for exploratory stuff. It's still work in progress. Maybe some functionalities has limited support, but I already find it like very useful and seamless. Also, there is Pluto support, but talk to me if you're interested in that. Of course, if you don't just want to play with parameters of your model, you can do optimization. The only change here is that we define the log likelihood function, and then I highlight in bold that we pass it to the accessible model. To the accessible model as the first argument. That's it. Nothing else in the model definition changes. The struct stays the same. They can be your arbitrary Julia struct. No need to kind of like specialize or like use some annotations in there. And here, your log likelihood and all your kind of model definitions, they don't care about flattening to vectors. They don't care about reconstructions. You don't think about vectors at all. You just think about your struct. How do you compute kind of loss or likelihood or whatever, and then you can just pass it to optimization.gl. It's a very thin integration layer that gets you your kind of model back. It doesn't get you back the vector, and no need to stop at optimization. You can do MCMC with exactly the same definition of the model. You also specify what are your priors on on which argument. And so now I only support pigeons, but it's a very thin integration layer. And again, as a result, so you don't work with just raw vectors of parameters anywhere. All your functions and the result as well, this is just your model, your model with different values plugged into it. So it is implemented in accessible models. Probably I should register it soon. This is very thin. This is like a really very thin wrapper around accessors. With all the Maki optimization and pigeon support, it's about 100 of lines total. And most of them, of course, are in package extensions to do these kind of connections between the actual object and the API of like Maki optimization pigeons. Integrations are easy to add if you, like, I guess maybe Turing makes sense as well, to work with more samplers. So it is really should be trivial to add, and it's really nice to have the same model definition. First you play with parameters interactively, then you quickly optimize the values, and then you can do Monte Carlo sampling, always the same model definition. So there are kind of other use cases. I was given a Maki extra talk yesterday, but basically it uses optics. If you define kind of mapping from your data to plotting attributes like X, Y, color. With optics, it can both give you automatic axis labels, because I mean optics know how to stringify them. And also you can get these interactions automatically, because optics know how to change a value in an object. They know how to create create new objects out of these. Yeah, I would say this is kind of just follows from what optics are. It works very nicely. And I think this will be the last kind of specific use case. It's given that optics are kind of just functions that are not opaque, like lambda functions, but inspectable. Kind of, they are just objects like composed function and base fix and whatever. There is also a thin layer, SQL collections, .gl, that converts kind of. This is code using just everything in memory, using kind of base Julia functions and CSV reading. And this is just with very tiny modifications. You kind of just add O here from accessors. It works without loading all the data set into memory. It works just converts it to SQL and only materializes the final result. Here, it's kind of uses only a part of optics. It doesn't use set at all. It just uses @o macro as a neat way to create introspectable functions that you can then nicely convert to SQL. So that's it about use cases. And my final part of the talk is the design, performance, and a bit on the future of accessors. So the main kind of constraints that we work with in accessors is to make it really zero cost everywhere where it's possible. It should be seamless, and it is seamless for users, although it's sometimes very tricky to actually make it work. Because optics, so if you have several composed functions and you want to set or modify, it needs to unwrap all these kind of chain of functions, and it heavily relies on recursion and the compiler being able to optimize this recursion. So whenever there are some changes to Julia compiler heuristic and limitations, I mean, they don't break performance tests in accessors that often, but sometimes it happens. And we need to take special care, and we do take that, to kind of limit the recursion to a minimum. Sometimes we have to kind of forgo straightforward implementations that should work in principle, but they are very slow in practice because of compiler heuristic mostly. Some cases of where it's difficult include especially like set all, so like setting multiple values, and recursive optics. They are really hardest. We haven't found a better way other than using multiple evals in a loop, or there is this kind of hash self-hash trick that works for some recursive functions as well. So if you are if you can help with making this code cleaner, avoiding generated functions, evals, and other hacks, and still keeping the performance, yeah, I would be happy to chat with you. Yeah, so that was the example of @eval calling @eval in a loop, and this is an example of where we need to use hash self-hash trick that I just randomly learned about from some discussion at functors.gl. Yeah, and this is kind of my summary. So the idea of accessors is whenever you want an object like the one you have, just with some part of it, like arbitrary part of it defined by some function, modified, that's just @set for any kind of reasonable function. The idea is to support as much as possible. It doesn't actually take a lot of effort. And this simple idea, it leads to really wide applicability. So I've shown these use cases from kind of different fields of Julia kind of usage, and a lot of natural extensions to accessors. The design is kind of aimed to be easy to use. I think it works. It is composable. I think kind of really impressive how it's possible to make it composable and not sacrifice performance, but it works and works stably. It is made, this composability and performance are made possible by the Julia semantics, the multiple dispatch, of course, and compiler optimizations. We crucially rely on compiler optimizations because accessors are often used in hot loops, like in optimization or elsewhere. And this means we could really use some more direct control on the compiler heuristics, such as recursion limits. I think I asked about that like on either Slack or on GitHub issues at some point, but yeah, I guess it's not trivial to add either. That's mostly it, just kind of like a glimpse into potential near future. So there is a single most requested feature in accessors, is to set multiple parts of a structure at once in one call of set or something. Currently, there is no kind of dedicated support for it, so you can just use whatever piping package whatever generic piping package you like with @set, and it works. There are some proposed variants on what syntax we can use to set multiple properties or multiple functions at a time. This is still kind of not decided, but really we regularly, definitely every year, maybe even more often, get a request of something like that. That's it from my side. Happy to answer questions or follow up with discussions afterwards. Thank you.
May I ask when a function f is unreasonable?
So sometimes you cannot just, it just doesn't make sense to ask a question, okay, like I want the object with f set to something. Like, I mean, if your f is, I don't know, your, let's say you define a loss in optimization, right? And you cannot just say, okay, like set me the loss of solution to -1 or like to 0. It just doesn't make sense. This is a kind of simple example, but also, I don't know, read file or like read doesn't make sense to set, right? So I'm talking about like these kind of functions.
How are you actually quantifying the cost of your abstractions? You said zero cost abstractions. Do you have like tests for that?
Yeah. There is like a separate file with tests, like specifically performance tests. They are both tests that everything is inferable, that there are either no allocations when there should be no allocations, or as many as if you would do the same thing manually. And there is also benchmark tools used in there. That's why from time to time, of course, for random fluctuations, we need to rerun CI, but generally it works pretty stable, and we immediately catch if something is broken in the Julia update.
Yeah, I'm really glad you touched on the the struggle between user convenience and developers. I would call them investments, because it gets more and more convoluted and becomes harder and harder to maintain. And how do you kind of do the policing? Like whoever contributes, you have to make sure their contributions up to the standard.
So for any kind of non-trivial functionality, we always add the new performance tests. But generally, you just need to keep an eye on that. If you just remove the performance test and wait for like 3 years, a lot of will break on the new Julia version. But if you do it like kind of whenever a new version comes out, there are almost always just like some tiny changes needed if needed. So I guess we manage.
Yeah, but you're introducing more and more tricks, and it gets harder.
So actually, like most of these use cases, at least, they don't touch on the actual kind of underlying optic implementation. They are just thin wrappers around. Like for example, like accessible models, it just uses get all, set all, whatever from optics. And it doesn't implement anything itself. That's why it's only 100 lines of code. What else? Kind of like all these use cases, they just realize that accessors.jl, that it's performant, and it compiles to the same code as if you do the same manually. That's why kind of dependent packages, they don't need to care about it.
Yeah, thanks. Any other questions? If not, let's thank Sasha again for the wonderful talk. Do we have the sparse matrix mini organizer here? Sorry. the sparse and graph computing. Okay, let's wait for 5 minutes, and hopefully the speaker will show up. Sparse and graph computing? Yeah. Augmented are you the next speaker or the augmented?
I am the speaker. Organizer is just by the door.
I'll wait for him.
Yeah.
For the augmented to introduce.
Yeah, yeah. I'm just gonna set up electrical connections or all that. Who's your organizer?
So which one is the augmented? Oh, sure.
At least one of them. There's usually two. The main issue is electrical, I think. I need more charge. And there's one behind me.
Yeah, there's one over there.
The thing is, are they long enough? So we'll see.
Are you chairing the?
I am chairing the session.
So yeah, here.
Oh, awesome. Yes, very sharp. I think we told everybody they had a little less time than they actually have. So
Exactly. Yeah.
you can use as much of it for questions as you want.
We have a runner for the.
Oh, that's great. Okay. Amazing.
And then I'll leave it to you. So yeah.
Okay.
So there is only this before the lunch, right? Lunch
Yeah,
break.
it's just this before the lunch.
Awesome.
I'm going to clarify to everybody that it's like, everybody come back after lunch. Like
Yeah, yeah.
I'll try and communicate this little.
That is not what I wanted, but let's see. That is what I wanted.
Very different topic.
20 years to... Seems correct, right? Jackets. I took mine out.
It's 11.
I don't know, what's the tradition here?
Do we start on time or we wait a bit? Wait a couple more minutes. People are still showing up. Julia time. Everybody always talked about Berkeley time.
Berkeley time is very sharp, though.
Yeah. Oh, like 10 minutes after every time, or?
Yeah.
Yeah.
In campus, it used to be that way. It still
Yeah, I
is.
remember that they were pretty strict about it.
That just means...
Between,
Just imagine it didn't... Like, 10 minutes is really warped. Time is really shifted there.
Is there an MIT time? Or
Yes.
is MIT just the actual time?
No, there is an MIT time, right?
It's like 5+ minutes. It's a little bit looser, I think.
yeah, it's not like, Berkeley time is like a real.
The problem with... The reason Berkeley time has to be that way is the class ends at the hour. So for the person to move to the next class, you need the 10 minutes walking time.
Yeah.
It's just not feasible.
Yeah, it's a pretty long campus.
After?
Hmm?
Classes are scheduled at the hour?
They're
They-
scheduled at the hour with no space in between.
So the assumption is...
But the assumption is they start precisely at 10 after.
Oh.
So all times in Berkeley.
We do the most chaotic thing, which is we have 15-minute classes, 15 minutes to get to the next class.
Yeah.
So the class times recess through the day. So like the first class starts at 8, and then so at the middle of the day they're totally random. They're like 11:40 is the start time.
It's like a doctor's office.
Yeah.
Towards the end of
right.
the...
The first appointments are actually on time.
Yeah.
By the end of the day, they're like 45 minutes behind.
Yeah, exactly. Well, brutal. I'm fine, yeah.
I think we're all here. I can go ahead and do a intro, just a quick little.
Do you want to use the microphone?
Yeah, sure. I have some notes. But I was just going to say welcome everybody to the Sparse and Graph workshop at JuliaCon. I think that, I don't know about y'all, but I look forward every month or so to like a new release in the arrays Slack channel in Julia. I think that like arrays and graphs are something that really motivate a lot of Julia programmers. And sparsity is an interesting topic to tackle like with a language. It involves a lot of diverse applications and interfaces. It's also a really performance critical aspect of scientific programming. And so I think Julia presents a unique opportunity to tackle this challenge. Julia has lots of metaprogramming features. It has lots of specialization capabilities. And I think that every time a new language is developed, people like to try new things and try new interfaces and do things a little differently. And so I hope today that we can reflect a little on the things that have been tried to tackle sparsity in Julia, and we'll also shift our focus to beyond Julia and ways that we can interact with the ecosystem of sparse computing at large, and also graphs. Okay, so our first speaker, the keynote speaker, Aydin Baluch, is a senior scientist at the Applied Math and Computational Research Division of LBNL, also adjunct faculty at the EECS department of UC Berkeley, and perhaps most relevant to today's is also currently directing the DOE Mathematical Multifaceted Integrated Capability Center named the Sparstitute. So with that, we'll let Aiden take it away.
Thank you, Will. Thanks, everyone. This is a pleasure to be here. A little bit of background about Julia and me. You won't hear a lot of Julia from me because I'm a little bit language agnostic, and I'm going to talk a motivating talk about sparse computations in general. And so there's not going to be a language choice. But I like Julia for a lot of reasons. And one of it is historical. The Viral and Stefan was my lab mates when I was a grad student. So I know I even know the funding that allowed them to bootstrap this thing when they first started. So it's a pleasure to be here. Okay. Past, present, and future of sparse computations. So we live in a sparse world. You can take probably 20 different examples. I'm just took 2. Right? You get a telescope, you look at the sky. What you're going to see is a bunch of stars sparsely populating the sky. And you have to realize this is a 2-dimensional projection on your eyes of a 3D expanding universe. So the reality is way sparser. And that's actually going to help us think about why tensors are even sparser objects than matrices, because there's so much more space there. And man-made things like internet is sparse. The brain connections, I can pull tons of these things. So we already live in a sparse universe, and some of it is by design, some of it is nature's design, whatever you call it, or just there's no other way to scale up with everything impacting everything else. A little bit about way personal history, right? This goes way behind, there is before 1990s of this, but, I was probably 7 years old there, so before that is kind of not really historian's concern. PD is partial differential equation, circuit simulation, numerical optimization, meaning whenever you call IP opt, there's a bunch of sparse solvers. This is the interior point optimizer, right? These have been there pretty much. All the engineering problems have been solved by sparse matrices under the covers. In fact, I had the pleasure to look at NVIDIA's cuOpt, and I kind of was surprised to see that a lot of the sparse mystic machinery was re-implemented. Somehow they didn't call, cuSparse or anything like that. A lot of the logic was there, handwritten in cuOpt, and how to transpose sparse matrices, how to multiply them, all of those. And in 2000s came the network analysis. I'm going to put a couple of historical things, what enabled them, but you can think of like PageRank and so on, started this thing. And then big data, collaborator filtering, text mining, all those things, that was another landmark, probably 2010s. And then deep learning, of course. Now we have graph neural networks, now we have sparse deep learning and quantum computing, all of those things use sparse objects. And I'm going to touch quite a lot of those things. If you just want to put some dates on these, there's the PageRank algorithm there that probably kickstarted network stuff. Sparse tensor toolbox that Temi Calder and Brett Bader, I think, published. Obviously not at the same impact as PageRank, but it created a lot of tensor analysis research. And they actually have a new book with Gray Ballard and Temi Calder on tensor decompositions, which is pretty excellent if you're into that kind of stuff. Okay, so what is sparsity? The first Nobel laureate in my talk will be Markowitz. In fact, he has a pivoting scheme that's named after him, if you open any sparse matrix book. There is debate whether his work on sparse matrices has anything to do with the Nobel Prize that he was awarded. But he had this quote, right? If you pivot carefully, then things will stay more sparse than vice versa if you don't pivot carefully. And how many of you actually are following when I say pivot? Okay, so we're good. We're thinking of Gaussian elimination. We want to, choose a pivot, and if you choose the wrong one in a sparse matrix, things will get dense. That's what he's talking about. And then how I define sparsity is really the property of having few non-zero significant elements. And this slide is there to show the scale of problems people really worked on. This is one of my favorite papers. I wish people actually did study on these kind of general computer science problems with the same attitude as Gilbert and Pills did. Here, you know, you'll see in computer science, here's a worst case input, and my algorithm matches at runtime, so it's optimal, and the case is closed. Whereas in practice, your algorithm will run differently on different inputs, right? So what you want your algorithm is to run as fast as possible given the input for every input instance. And this, for example, this work exactly does that. What does it do? There is a certain number of sparse flops the algorithm has to do to compute the answer. What that means is two entries are multiplied, both of them are non-zero. That's a sparse flop. And there's no way you can do this any faster than that. Plus the data structure setup. There needs to be some little data. And the algorithm does exactly that no matter what the flops is for a given matrix. And these can be arbitrarily different numbers for two different inputs. And that would be crazy, right? If someone told you that, you know, when I'm computing a maximum matching on a graph, there is a minimum number of augmentations I need to do, and my algorithm runs exactly as that many augmentations for any input you give me. That would be a crazy result, right? That's kind of like that. So the idea is don't do redundant work and count sparse flops, stay as close as possible. Not always possible, but that's the goal. And the scale of the problems were like this. The number of rows and columns is a couple thousand, and number of non-zeros, which they call M, is doesn't go beyond 20, 30,000. So we're living a very different time. I don't know if I have a slide for that, but I do. So what is the thing that Willow talked about, the Sparse-Tooth? I am directing a center that works on sparse computations within the land of Office of Science. So the focus areas we have are networks, tensors. Networks we broadly define as graphs, hypergraphs, topological objects, any of those things, topological data analysis, and obviously traditional matrix computations. And the sparse-tooth definition we have there is a little broader than what I talked about. It's not just about non-zeros. It can be data sparse as well. If you've heard about that, which means your matrix can be low rank, and you can just represent it as a bunch of outer products, that kind of stuff. We are actually running a networks workshop. So if you're interested in coming to Berkeley in November, I actually should have put the link. The website is up. So I should put this in. I have not posted it in any group newsletter or something. So what do I mean with this long mouthful thing, MIMICS? MIMICS stands for multifaceted mathematical integrated centers of something. And then the last T, capability center, got it. So what does that really mean in terms of multifaceted? So when you have a problem, you usually have multiple layers of things that you need to work on simultaneously to make it work. And I'm going to use a couple of examples. The first one is one of my favorite works that I'm going to expand a bit. So we always have worked on, this is one of my favorite operations, multiplying two sparse matrices, right? I call it SPJam because it rolls in the mouth. Some people call it differently. And we do develop new algorithms for distributed memory, for shared memory, communication avoiding, all that stuff. But then years ago, maybe 7 years ago, 6 years ago, 7 years ago, a collaborator came and said, we want this Markov cluster algorithm that we use for clustering protein sequences to be distributed and much faster, because we need to do this in really large scale. So we developed for these guys HipMCL, and one of my collaborators also developed an iterative version that I'm not going to talk about. But HipMCL uses all these machinery plus more that has in SPJam and other sparse matrix techniques to be able to scale to do supercomputing scale, also GPUs and everything. And then that actually got used in a paper to discover novel protein families that I'm going to talk a little bit. So you're working on applications, you're working on algorithms, you're working on computational kernels, pretty much, maybe not simultaneously, but over a time span, all of them. Another example is work that Richard Ledick have been working on, a former research scientist. It's metagenome binning. You get a bunch of sequences assembled from a lake sample, let's say, but you don't know what sequence you assembled comes from which bacteria or which archaea, all these living organisms inside the soup. And you need to bin them. So there's a lot of deep learning going on there. But one of the performance critical parts is after you get these vector embeddings from deep learning, you need to cluster them. And the algorithm that uses, that works very well there is HDB scan. Well, if you look at that, so then there's this performance limitations of this, such as the dendrogram construction that sparse tooth researchers have been working on how to accelerate, and which, if you think about it, is actually just a special case of a general thing that sparse tooth researchers, such as my colleague Dmitry Morozov, have been working on, which are based on persistent homology computations. And that's a whole different, really nerdy, nice area if you're interested. So that's what I mean with like multifaceted and integrated. So now I can kind of go into some specific examples that I find sparse computations in action. Okay, let's say you want to discover this thing called a protein family. This is a really important part of life where it is a group of proteins that are descended from the same ancestor. Like I have hemoglobin that carries oxygen to my cells. It turns out soybean has an analog, homolog, technically, and that also carries oxygen to its cells. You can guess that the hemoglobin of soybean has little familiarity left through evolution to mine, but it's still the same function. So how can I get that? How can I figure out this whole group of all these homologs of this protein across all evolution? And I will have to do this not because I'm all that interested in a new organism's homolog of hemoglobin. That's not that interesting. What I'm really interested in, I get a sample from an ocean that I haven't sent ships before. And now I see a big family of a couple hundred members. That means something important. Some important protein is there. It's encoding some useful life purpose. It's encoding some enzyme. And that can be useful many different things. It can help me capture more carbon dioxide in the soil. It can help me develop some things that can break down biofuels faster. It can do a lot of things. Now, what I'm trying to say is the things that I don't know that I can discover with this method is more important than discovering things I already know and putting them into buckets. So the novel things are more interesting. So in order to do that, I use usually sequences because they're abundant. Protein sequences are abundant. So you start with them and you build a big graph called the protein similarity graph. That's already a very expensive computation. And I'm going to talk a little bit about that. But the point that I want to say is that's actually, we use sparse matrices to do that as well. And from there, you have a graph. Now, we want to cluster this with graph clustering algorithms that you can use, of course, millions of them, but not all of them give you the same quality results. And our collaborators were adamant that we needed to use some version of MCL, which is, I'm going to show that it's actually also based on sparse matrices, and it's always been. So what does it result? You start with this big data set. You get all the transcriptomes on Earth, find all the proteins. This is standard translation. You map them to all the known databases in the world. A lot of them go away because I already know them. Now I care about the things I don't know. I do, this protein similarity calculation many to many. I get over 500 million protein graph with lots of edges, 5 billion plus. And I run this algorithm for 4 or 5 hours on the largest supercomputer I can get, which uses a quarter of the whole machine. Sometimes it crashes, so I have to restart this, and no one knows what happens on the software stack. But the result is it more than doubled the number of known protein families. And I never thought that I would get a paper at Nature at a nice place as an author list. And a year later, it actually turned out that one of my co-authors is a Nobel laureate. But that's for the second part of the talk, which is actually completely unrelated to what I'm talking about. Not completely. It's all sparsity, but it's related. I'm talking about David Baker. Somewhere over here, I can't reach out. Maybe there's a mouse button. Yeah, David Baker. You'll see his picture, I think. So what is happening under the covers? There is a big sparse matrix machine similarity calculation. This is actually, you can think of this as documents too. Let's say you wanted to find near duplicate documents in internet. How would you find it? Of course, there's all these techniques, shingling, locality sensitive hashing. But here what we do is we use basic k-mers. K-mer is a subsequence of length k. You find all the k-mers, you map them in a sparse matrix, so you get this large object that is proteins by k-mers. If a protein includes that k-mer, there is a 1 in that location. Otherwise, there's nothing. And then if you multiply this matrix with its transpose, which is the computer inner product gram matrix, you find all the pairs of proteins that share a certain number of k-mers. And all this is actually doing with existing algorithms that I know from sparse matrix literature. And they're optimized for this distributed memory machine, this GPU, and so on. So I don't need to rewrite all of that sparse matrix construction, multiplication routines at all. Anyway, these are just like fancy numbers of how many things have happened. We got this work led by Oğuz Selvitopi a couple years ago, was a Gordon Bell finalist. That's the supercomputing community's biggest prize, if you probably know about it. And there was a surprising moment there because, by that time, Frontier was coming. It wasn't kind of completely open, but all the submissions were running on Frontier. So HPC wire people were like, there's another finalist, we can't find what machine they've used. And I kind of said, well, we just used the old Summit. And they were really surprised that we actually made it to the finalist list with a machine that's 6 years old. Well, of course, we didn't win that one. We should have gotten access to the new machine, but it was still a good nod on the techniques the committee must have liked. Okay, so what's happening in macro clustering? I told you there's sparse matrices there, and I kind of told you believe in me. But the reality is, here's the actual details. The algorithm does random walk from every vertex. So every step, you're making your 2 hop neighbors your 1 hop neighbor and normalizing the probability mass around you so that it sums up to 1. And then you do an inflation expansion thing so that big entries are pushed up, small entries go down, and you can prune the network so it converges to clusters. That's the main idea of this algorithm. The trouble is, it became pretty obvious for us that we cannot square this matrix at all, because this matrix is already, what did I say, 500 million entries? Now it has more. It's been increasing. And it has more than 1,000 non-zeros per row and column. And if you square a matrix like that, you'll get more than 1 million non-zeros per row and column if you're lucky, which means if it's identically and uniformly distributed, but it's actually worse. So let's say if you're lucky, you have 1 million times 500 million times whatever bytes it takes. It's more than my whole supercomputer memory combined. So that's not going to work out. So we do some, of course, partial computations and as much parallelism as possible, as little communication as possible. So there's dual objectives. This work was led by Ariful Azad, now at Texas A&M University. So people's careers have moved on significantly. So the summary is both of these pieces of this pipeline, both the construction and the clustering actually uses sparse matrices, right? And we continue working on this problem. When I say we, my postdoctoral fellow, Yusha Hang, had a paper in SC last year, and Ariful had a paper with his students as well. So different pieces of this. The research continues. And then this has interesting stuff, more outcome. But that's biology. Maybe you don't care that much. I'm going to move on to the next phase before I run out of time. So there you get a bunch of more pictures. So I said David Baker as a Nobel laureate, but the other half of that award that year in chemistry went to these 2 fellows you probably know about, right? Demis Hassabis and John Jumper of AlphaFold 2. Particularly, it's been called for AlphaFold 2, but some people say it's generally for all of the AlphaFold. Hi there. Good seeing you after so long. So if you look at the AlphaFold 2 paper, it's really dense, and there is you know how these science papers work. The results are in the main page. You have to go get the actual methods section. And there's this Evo former, which is a gigantic thing of essentially a graph neural network. So that's one use of it. And lots of other areas, power grid materials. I personally worked on the particle physics problem, protein problem, and lots of people at the laboratory that I work on worked on other pieces like materials and so on. But what's really happening when you look at a graph neural network training is you have two options. How many of you actually looked at graph neural networks recently? Lots of people, okay. So you have basically two options. You can do full batch training, or you can do, this is for training only, for this, or mini batch training. I like to contrast this to CNN so that the challenges are obvious. In a CNN, you have this beautiful property that all these little graphs are independent, all these little images are independent from each other. So you can just get a subset of it, compute your gradients, and then update everything, and then move on to the next batch. There is issues about convergence, if you get the batch too large, and so on. But fundamentally, those images don't depend on each other. Whereas in a graph, especially if you're training on a big graph, I can't just get a small subset of vertices, get a neural network of 4 layers, and hope that I'm going to update my gradients in time proportional to the number of vertices I picked. What ends up happening is I end up touching almost all of the graph. So I lost all the benefits of mini batching if I do what's known as a vanilla mini batching. So, which means, you know, just take a bunch of vertices and do learning around them. So to solve this, there are two options. One is full batch training. So you don't do batching. You try to train on the whole graph. This is, you know, optimization people, I don't think their names are around that much. This is the good old gradient descent with the whole data set. It's possible. It has memory issues, limitations for that memory. Basically, that's the main issue. And sometimes it converges slower per epoch than you would do with the stochasticity that you get. The other alternative is to sample this graph while training. So you don't train on the whole graph for each entry in your mini batch. You only consider a subset of its neighbors as opposed to all of them. That kind of avoids the network explosion. So we build a framework using sparse matrix techniques, and everybody uses sparse matrix techniques. When I say sparse matrix techniques, is all the knowledge that we had from communication avoiding algorithms and the primitives that we know how to map these things. The short story there is full batch training is really about a graph convolution, at least, is looking at your neighbors, looking at their feature vectors, aggregating them through some function that I decide, and updating my own feature vector with another function I decide compared to the neighbors. Right? At every iteration, this is what happens. And there is, of course, there is learnable weights that are also, you know, mixing these things up. But fundamentally, all of the time is spent on this update, which is really a sparse matrix that represents the graph multiplied with a dense, tall, skinny matrix that represents the feature vectors or embeddings and so on. Ben is here. So Ben has worked on this sparse matrix, tall, skinny, dense matrix multiply. Here's Ben. And you know, we looked at different algorithms and different programming models like RDMA and MPI, so on that work. And that's been used in this paper in Reducing Communication and Graph Neural Networks that look at all these possible algorithms of 1D, 1.5D, 2D, 3D, how to you know, partition your communication grid. Okay, that's for full batch. What do you do for graph sampling? The trouble with graph sampling is there's many methods. And there is actually broadly classes of them. So there is node-based sampling, which is for each node in my active batch, I can look at a fixed number of neighbors. But that creates redundancy if other nodes in my batch share similar vertices. So what you can do is you can do layers-wise sampling. You can look at, I have 100 vertices in my active batch, and their collective neighborhood is this. And I'm going to sample from that collective neighborhood in proportion to the number of paths that each vertex is reachable to. So that really becomes a lot of sampling. It's fun, right? You compute these probability matrices and how to sample. So we built a system that can do both node-wise and layer-wise sampling. Both of them use sparse matrices. And you represent your probability mass in sparse matrices. You batch. That was one of the tricks that we had to use. I'm not showing here. The main operation here is you have a big graph that you're computing on, but you want a smaller subgraph. This whole sampling thing is really extracting a small subgraph. You don't need to physically extract it. You can only logically extract it. And then you can call the existing full batch training method if you want. The trouble there is I know no algorithm that can sample, extract a subgraph or extract a submatrix from a large matrix in time proportional to the output. Most of them just end up touching a lot of the input. And if I do it for every epoch when I go over the data, I spend all my time touching the input. So we could have spent a couple of years trying to find out output-sensitive algorithms. Instead, we did the fastest, more engineering method, which is I'm going to sample as many batches at once as my memory allows. So I'm going to sample 1,000 subgraphs with one operation, so I'm only touching the big input graph only once, as long as that's within the memory. And I'm going to train on these little graphs in sequence, so I don't need to resample. So that's what we call a batch sampling. That makes this sampling graph much wider, so you stack all of them. Speed ups over Quiver, which was the best thing out there when we looked at this. This is work led by my student with Kat Yelik. His name is Alok Tripathi. He just graduated a month ago, so it was, and joined one of the AI startups. So what are we seeing in the results is good. So like that's not the point, right? The point is sparse matrices are pretty much powering all of graph neural networks. And this is not just our system. If you find PyTorch geometric, you'll see that it all was a bunch of sparse matrix machinery underneath it. So this is the last slide before I go to future, which is, I guess, a good timing. How many of you have heard about this term called equivariance? Yes. Yes, OK. So this is a nice property of a function. It's kind of slightly different than, so I apply a function to my input, and that means I'm also applying the same function on the output. If there is a vector valued function, if I, that function is kind of rotating the input, it should rotate the output the same way. And those are really nice when I work with chemical models like atoms and so on. So people use these, and don't start a debate, because at least I know that in machine learning community there's two camps. One of those people really like to build in equivariance into their networks because it allows them to train with smaller amounts of data, and more efficiently. And the other camp will say, they will cite this blog post, which is the bitter lesson. I don't know if any of, yeah, which if you throw in enough data and compute on this problem, the system will learn the equivariance rules you're trying to enforce. So you don't need to encode them and waste time on computing them. Anyway, let's close that chapter. What we wanted to do is, we don't have a stake in this game all that much. We wanted to level the field because tensor computations within the equivariant networks were really expensive. So what we wanted to do, they don't need to be expensive. We can actually accelerate them significantly. So my student Vivek developed this thing called open equivariance. Hopefully that's cited. A covariance, yeah. Way more stars now. The slide is old, which accelerates these foundation models, chemical foundation models, significantly. You can see that E3NN is one of those systems out there. It's not a foundation model, but get the same results. And the results you get from open equivariance is green, and the higher is better. These are speed up numbers. So you can run these things way faster than you used to. So that's also using a lot of sparse matrices, but it's like a kind of a sparse matrix that I've never seen. You know exactly the coefficients and the structure beforehand. It's beautiful, in fact, to visualize. I don't have it in the slide, that you can lay out your memory and create the code for it with the instructions beforehand. So that's why he's using like JIT. So there is no like dynamic CSRs and whatnot. You know the index beforehand, you know the coefficient beforehand. So it's kind of a beautiful problem case. And you can reorder all of those things because you know it at compile time technically. Okay, the future. Where do I think this is going? Maybe long list, but the trends. One of them is data size, right? This is a couple of examples. The things have been getting larger and in the public domain. There is, if you work on real companies, the chances are things have already gone way larger that no one is willing to talk about them, right? So remember the numbers that I've coded in the paper that I cited in the first part of my talk. We are many, many orders of magnitude larger in terms of the problems we need to deal with. And we often need to deal with stuff that we can't materialize in RAM at all. So we need to use some techniques that allow us to process them without ever expanding them. Architectures are not favorable for sparsity. That's probably been known for a couple decades by now, but it's getting ridiculous that the HPCG, which is a sparse benchmark that is also used to rank supercomputers, are getting wonderful peak performance compared to the top 500, which is using high performance LIMPAC benchmark, which you can say it's irrelevant, but clearly not favorable. And then there's this thing called twilight zone sparsity, which is one of my favorite words these days. I don't know if anyone else have used it. You can read the large code and so on, but what I'm trying to say is our codes in sparse communities, whether it's graphs or tensors or matrices, have been optimized for the cases where sparsity is the only way. No sane person will get a matrix of 7-point stencil and try to put it in a dense matrix, right? So there's no competition. We're competing with ourselves. Here, you're competing with the tensor cores and the dense matrix multiplication in the land of large language models. Heavily optimized, 4-bit. Okay? Now you get your index value there as a sparse matrix, you're in big trouble. Because now as your index value is 8 times bigger than than the floating point value tensor cores are multiplying on. So not to mention that they're getting 90% of the peak. So, and then you need to work on a sparsity regime which is not like 7-point stencil anymore. You still have a lot of non-zeros left. So we need to develop new data structures and new algorithms for this twilight sparsity zone. But there is hope. If you can target sparsity that's 95% to 99%, there is a lot of juice that can be, it's in activations, it's in weights, and nowadays you'll see that it's in, I'm actually going to come to this, in other parts. Let's talk some of the most promising directions for my very personal research. One is I like randomization a lot. Randomized linear algebra have changed a lot of things in dense linear algebra. I think it can have a similar impact on sparse computations, not just in linear algebra, but in a lot of other places. So here's one example that a student, Tianyu Liang, has worked on. Too much plots, but the main idea is this. This has actually been known. There's a big Julia package, I think, sparsifiers.jl by Dan Spielman. This is actually like trying to do what Dan Spielman does in GPUs in high performance, with a bunch of tricks to make it go faster. So randomized sampling allows you to avoid the clique formation. Instead of when you eliminate a vertex in this game of sparse Gaussian elimination, instead of forming a clique among all of its neighbors, you just sample a tree, statistically randomly distributed tree out of that. And that creates a lot more parallelism. That avoids the memory problems. But it creates a lot of new problems. You can't predict the structure beforehand because you don't know what tree you're going to sample. And you don't want to be dumb and say, I'm going to assume the worst case and I'm going to assume the clique, because then you don't gain much. So lots of dynamic dependency tracking that happened in this work. So it's on arXiv if you're interested. But that's just one example. Randomization has been used to accelerate a lot of things. So hopefully it's going to continue. Sparsity in AI. So there's a wonderful survey. It's a bit old now because AI 4 years is too old for anyone to care. Maybe 5. Thorsten Hoffler and company had a big survey on sparsity in deep learning. And they have this nice classification of model sparsity, which is the weights and so on, and ephemeral sparsity, which is like activations and gradients. Right? I kind of call it because a little old because I think it's now missing the most important sparsity where people actually win. A lot of models that were sparse there didn't quite win. They kind of came close. They were 20% better, 30% better. In general, it wasn't worth all the engineering. But down there in sparse attention, actually, in DeepSeek papers, if you look at it, in their native sparse attention, 6 to 8 times faster than dense attention. It's insane to me. It's kind of buried in there. What is the sparse attention when you're computing these attention scores between words in your model, tokens, sorry, not words, right? You don't need to apparently compute all of them. You can get away with a subset, either a static subset or a dynamic subset based on a certain statistical score, importance score. So that allows you to get away without the n-square computation. But there's much more examples. The activation sparsity work that seems to reasonably converge this with very few non-zeros. There's hardware support for 2 to 4 sparsity, which is kind of limited. I wish it was better. If you don't know this, this is for every 4 entries in the matrix. If 2 of them are non-zero, you can run exactly the same speed in some sense, in the time proportional to 2. So you can kind of double the speed. In practice, it doesn't get that close, but it still is favorable. The problem, of course, is that's still 50% dense matrix. That would only work there. And the last trick is very typical. I'm not going to spend too much time. There's still a lot of parallelism we can extract from these problems that have been overlooked. Why overlooked? Right? You want to solve A minus B, A backslash B. You reorder your matrix. You factorize. You solve. Traditional wisdom 10 years ago, solve takes all the time. Sorry, factorize takes all the time. Don't worry about the other steps. Whereas now the factorize is GPU accelerated, distributed, because it's easier to parallelize. And now you benchmark these things, and then you see that a quarter of the time is going to reorder this matrix. It used to be like, this is 5%, who cares? So based on Amdahl's law, with the trend, now you have to start working on these problems. And this is a work that another PhD student, Yan Shang, has done to extract parallelism from the famous approximate minimum degree algorithm.
Are you saying that the factorizations are taking more of the time?
No, always. Factorization always takes more time, but it used to be that it was 98% of the whole pipeline. Nowadays, you can see it. So what are you looking at? cuDSS is the latest direct solver of NVIDIA. It's way faster than their previous iteration, as you can see. And the AMD, which is serial because no one really knows how to parallelize this high dependency problem, So these are different phases of the process. It's about a quarter of the time that factorization takes. It's no longer like 1%. So that's what I'm. A few parting thoughts. I wanted to connect this to the graph plus and sparse plus you might have heard about. And these are like my airplane thoughts. I'm kind of feeling like, as someone who spent a lot of time in graph plus and not so much time on sparse plus, admittedly, with the success of large language models, the syntax choices and the standardization matter less. We're not really doing this thing so that people really implement this thing with the standard so that it's all compiles without changes anymore. Maybe intentional was like that a decade ago, because I'm pretty sure I can ask an LLM to convert my code to one vendor's syntax to another vendor's syntax. It's not the problem anymore. But they're still important because it tells what the community cares about for the researchers to work on, the companies to implement. We are still telling them these computational primitives and these kind of options matter to the practitioners. So they still have value, but maybe we shouldn't kind of care too much about the syntax and the standardization parts. Again, very personal thoughts. A little bit of a wish list. It's all one topic, actually. I started listening to sparse compiler work with a lot of smart people, including Willows. And dense linear algebra compilers obviously are way ahead because they have a much easier space to work on. But then you look at it with all the flashy dense linear algebra compilers that reorder computation on paper. And the best thing that came out to reduce the runtime of LLMs came from someone's own ingenuity again. Why sparse attention and its variants are not discovered by these smart compilers? Well, it's not a big transformation. All it's doing is certain tiling plus a little algebraic manipulation. Really one, I think. So I'm interested to hear how do sparse compilers fare in practice these days. Do they just help me implement the known data structures and algorithms faster on a new architecture? Or can they discover things novel? What is their limitations of fusing different operations? Those are actually things that I care a lot about. And I totally do not want to implement fused operations. One sparse operation is sufficiently complicated. Anyway, sparsity is a common problem. This is all about the research project that I'm leading. In the couple of slides, not that important. But I think sparsity research is changing with the new challenges from architecture, data, and application sides. AI is one of them, definitely. It's going to bring a lot of money and a lot of exposure if you do it right and help them. You can check out my group or the Sparse Institute. The group is passion.lbl. Hopefully the link is correct. And thank you for having me.
All right, let's everybody dive in. So I think now we'll do a couple questions. And then after questions, there will be a lunch. This room's going to get taken over by a different thing. And then after lunch, we're going to finish the rest of the workshop.
This room is just scheduled for that because there's no reason.
There's no good reason for it.
There's a small lunch that if you want to meet people from Temple Capital, you can go to that. But otherwise, it's just as it was yesterday on Tuesday, just sort of wherever nearby you'd like to get lunch.
So let's do questions. Does anybody have any questions for Ivan?
So on one of your early slides,
for the online audience, do we want to?
yes.
Oh, there's online.
Just repeat the question.
Oh, yeah. Yeah, thanks for the talk. So in one of your earlier slides, you showed basically some classic sparse matrices from the 80s, and then the new scale of matrices that we have in the Sweet Sparse Matrix collection, right? Yeah. And those matrix collections have evolved over the years and played a big part in how people approach optimizing kernels, what they focus on. There are a lot of papers that just run every matrix in the Sweet Sparse Matrix collection and then look at their speed up over existing methods. People debate about whether that's the right thing to do. There are questions. But with this new twilight zone of sparsity, do we need a new data set, or do we need to be adding data sets to the sweet sparse matrix collection? And what are the right sparse matrix data sets for the future to make sure that we're optimizing for the right things?
I even have notes from some, there was a sparse benchmarks meeting that got split into lower bounds and benchmarks. And one of those, I was starting to kind of create a Google Doc to share about what would a good benchmark should cover, right? The problems from graphs, problems for AI, sparse problems from physical simulations. The part that's really the hardest is, I think, the real problems in still simulation space. I think AI, we can generate those matrices by getting a large data set and playing with them. Graphs, we know what we do. But a lot of the problems that real companies solve, somehow don't end up being on this service. And I don't really know how they end up being in this service in the past to begin with. Maybe Viral knows the history a little bit more. It's insane that some Boeing company allowed some their stiffness matrix or Audi into this public domain. And nowadays, I understand that nothing new comes out of that.
No, I think it was a different world where people were, there was individuals, right, not the Boeing companies that did it. And companies have now clamped down and, it's just, you saw the same thing with LLMs, right? In the early days, everything was open. Now that there's value, no one's going to release anything more.
You get the weights from DeepSeek. The biggest open source. There's Llama. There's exceptions. In this one, there's no exception. I don't get any new data. We still run on matrices from 20 years ago, the best case. And they're not really that much representative. Because if they were representative, why would you think that NVIDIA would start a completely new direct solver with multi-GPU support? Like nothing in that sparse suite collection requires that much compute power. So there is clearly some customer base there that matter, right?
Sometimes there isn't a signal in these large company decisions, though, so,
I think they might. They seem to be small enough that, Google is 100,000 and they're only 35. I feel like they're still a little bit in that space. I wish, I can create this class of them, but I can't fill the real simulation space like that. That needs another willpower from other people, companies, so on.
Are there other questions?
James, you wanted to, but didn't.
I was going to participate in the extended discussion.
I think you should, to be honest. I don't know. That's up to the...
If there are no other questions.
Yeah, please, go ahead.
Okay. Yeah, just riffing on that, the companies aren't providing new stiffness matrices, but academic finite element is still proceeding at scale, right?
Yeah.
Like we're still getting bigger and bigger finite element meshes.
So why this is not getting updated?
Yeah, and I think I think they're not proceeding into the sparse matrix collection, but then it's a similar phenomena to you go to a linear solvers conference and it's all heat equation, Poisson problems. It's not real multiphysics, right? There's so much to go from the linear algebra community to the actual computational physics community, right? That gap is huge, and I think it's possibly getting bigger as the two fields become more specialized and more distinct, right? As you become you can be a sparse matrix person, not because you started as a CFD person or a structure, you're not starting as a structural mechanics person and being like, oh, I need to learn sparse matrices. You can just specialize in sparse matrices, right? So as the two communities become more and more specialized, I think the gap between people who are doing real finite element and people who are doing real HPC linear algebra is getting bigger.
That's not great, but
ominous.
Yes.
Yeah.
Are there any additional questions? I can ask one. So we're all here. Some of us are. dream of a better, thank you. We dream of a better way of programming with, scientific applications, programming in sparsity. What role do you see the programming language, not Julia necessarily, but the programming language having to play in the future of sparsity? What features would you wish for? What features present challenges?
I think that's a great question. I think it goes back to this bottom of wish list. Whatever language allows the compilers more freedom. I don't foresee myself in 10 years writing multi-frontal code. I think the machine will write it, and I will probably still have to direct it. I will need to know the concepts. I will need to understand pitfalls and all that stuff. But I'm not going to be generating the code. And 10 years is really generous. I think I will stop generating code way before that. So the question really becomes, what is a language that's easier to interoperate? What's a language that's easier to maybe tile things, parse things, and work easier as a compiler or code generator? I think that's, again, all hinging on the assumption that hand-coding life is not going to matter that much. So what does it mean for Julia or other languages is, I don't actually know that. At some level, I feel like maybe, is it possible languages will stop mattering? That's not possible, right?
There's the famous quote, right, that programs are meant to be read, but only incidentally to be run.
So it's like education, pseudocoding?
Yeah, no, I mean the point being of abstractions, right, that you always need more abstractions, and eventually the LLM will write something, but someone has to read it, and the LLM could write a multi-frontal code in assembly, right, but you're not going to read it.
I can barely read the handwritten C code. What do you?
What may be, and hence the rule for languages, right?
Yeah.
That if there were better abstract tools, like the dense linear algebra compilers, right? Like your wish list, right? Maybe there will be sparse compilers like what you would.
Yeah.
And I think there will be more of these things rather than less with LLMs.
Yeah, that's actually a great point. Yeah. NVIDIA was talking about this qtile thing. And I'm like, finally, I can just do a little bit higher level in CUDA if I'm working on matrices, dense matrices, right? So nobody solved this product yet, but they've talked about it, I think. So it's coming sometime. That's kind of going that way, maybe. Like higher level things where you work on blocks and not individual memory elements.
I think that's a great place to leave off. Thank you, Aiden. And everybody come back here around like 1 p.m., right? 1 p.m.? 1:30.
1:30.
Okay, yep.
Thank you.
All right. Thank you, everyone, for attending. This is the second half of the sparse and graph workshop in Julia. Our first speaker, Huda Nassar, is a senior computer scientist at Relational AI working on graph algorithms. Huda earned her PhD from Purdue University.
Okay, let me try. Can everyone hear me? Okay, good. Hi, everyone. So good to see so many of you here. First, just a quick intro about me. My name is Huda Nassar. As Willow said, I work at Relational AI. What I do at Relational AI is build graph algorithms so that our customers who want to use our product, if they want to run graph algorithms on Snowflake, that's basically the graph algorithms that me and my team work on. But for today, I'm actually going to talk about something completely different, still graphs, but nothing related to Relational AI. I'm going to talk about the graph of Julia, and just a quick disclaimer in the beginning. When I first started preparing for this talk, I had in mind to talk about more in-depth graph algorithms, how they're easily implemented in Julia, how Julia is really well suited to implement graph algorithms. And to do that, I wanted to get a fun data set to work with. And that fun data set ended up being the package dependency graph for Julia. But then I realized that data is so valuable, it's really, really fun to explore this data. So I kind of shifted the talk a little bit, and I'm talking more about the data and less about the algorithmic aspects of it. But I'm sure in this mini symposium, there's a lot of talks about algorithms too. So you'll hopefully get a bit of everything. And this is work with my PhD advisor. I guess he's continues to be my PhD advisor, and someone else, Claude. I don't know what's the best way to attribute recognition to AI assistants these days, but Claude helped a lot with this presentation, and I'll call out where Claude helped. Okay, so there will be three main components for this. Actually, let me set a timer before I forget. Okay, there will be three main components for this talk. I'm going to cover just kind of the relationship between graphs and linear algebra a little bit. I know that we have a diverse audience. I know most of you do know the relationship, but I just want to make sure that whoever doesn't just kind of sees the connection early on. And then the bulk of this talk will be about the Julia package dependency graph. We'll just kind of experiment with a few graph algorithms on these graphs. I would love for this part to actually be more interactive. So if you're sitting and you're like, oh, can we try this thing? I have the code ready and we can run things. I'll run things towards the end of the talk anyway. So feel free to ask these types of questions. And then at the end, I'm just going to end with, well, the demo will be kind of also in the part of the Julia package dependency graph, and then I'll talk about some notes and next steps. All right, so graphs and linear algebra. Just take a few minutes to talk about this. This is actually a screenshot I took yesterday from a talk I gave at JuliaCon in 2016. And back then, I was talking about a new package that I was working on called Matrix Networks that is also a graph algorithms package. And what I was kind of trying to make the point there was many operations we want to perform on networks or graphs are, in fact, linear algebra. And you can see a bunch of network operations you might be interested in, and maybe the most familiar to people is ranking, example, PageRank. PageRank is nothing but a linear algebra equation. And so because a lot of the problems from graph theory maps so nicely to linear algebra, we can actually use linear algebra to solve them. And the fun thing is that the one thing I would add to this title is that Julia is pretty good at linear algebra, and that's really what makes it so attractive to write graph algorithms with Julia. And just to make the point a little more clearer, I got this example from a link that I linked below. But basically, the idea is if you have these, you can think of matrix multiplication as traveling along paths and graphs. So if you have, this kind of bipartite graph between the green and the pink dots, and then another bipartite graph between the pink and the blue dots, if you want to compute this mn, and let's say I want to see the distance between the path between x1 and z1 here, basically this node here and this node here, that's the value over here, and that's the edge, the number that will be on this edge here. And that's really nothing but -1 times 5, that's -5, plus any other way I could reach z1, and that's the only other way is 2 times -7 in this case. So it's really 2 times -7, that's -14, plus -5, that's -19, and then that's how we end up with MN. So matrix multiplication, for instance, and graph traversal are very, very, very tightly connected. And there are so many problems like that. All right. And with that, I hope everyone is on the same page at this point. Graphs, matrices, similar. Julia is good to write graph algorithms because it's good to write linear algebra. So we're in that space right now. So let's talk a little bit about this Julia package dependency graph. I'll be switching back and forth between slides and demo here, so just bear with me with the screens. All right, so this is where all the code is, Julia package evolution. You'll see contributors here. This is one call out to Claude, because a lot of this started out as trying to vibe code. And this was a really cool project to actually do with Claude, because there's just like a lot of ways. It's interesting. Like there were a lot of ways where like things could have taken us much longer to actually get done, and Claude would do it just so quickly. But there were a lot of pitfalls, for instance, as well. So one pitfall was like this understanding between the general and metadata.jl and trying to explain to Claude what happened there. Like some packages are, you want to get them from the Julia registries, and then some want to get them from another place, and like the formatting is different as well. So just wanted to explain that to Claude, and that took a little bit of time of back and forth to get this right, but that it was right at the end. There's more than 12,000 packages, as some of you might know, in the ecosystem. So all of this data is represented in the data itself. You will see there's a monthly snapshot. So since 2012. There's literally a monthly snapshot up until May 2025, where you can say, okay, let me just grab the graph of dependencies. And they're all indexed the same way, so you don't need to do any mappings. And you can literally just compare a graph from 2012 or 2013 with a graph from 2025. I want to click on it just to make sure I haven't missed anything major. Yeah, so tracking the package dependency over time. Complete history. There's a transition. There's ways, instructions on how to regenerate the data as well. And this is kind of how it works. We first identify the relevant commits, both in registries in each time interval. And then, yeah, we basically create this consistent package index across both registries so that we have the same packages basically having the same labels, generated sparse adjacency matrices, i.e. graphs, for each time point using the consistent index. And yeah, basically, and then if you go to matrices fixed, you will see, oh, that data is actually not here, but I have it on my, I'll show it in a second. Okay, I think that was too big to put here. But anyway, there's instructions on how to generate it, just basically following steps 1 through 4. Okay, going back to the slides. I feel like I just lost my slides. Oh no, they're here. Okay. So this is just kind of a high-level overview of the data itself. And so with that in mind, we basically have, at this point, snapshot at every month. And you can think of all sorts of questions to ask about this data. The first one that I think many of us could think about is PageRank. PageRank is a very common graph algorithm that I'm sure hopefully most of you know about. And it's an interesting way to understand importance and influence in a network. And my favorite example to try and illustrate why PageRank is relevant is like, if I want to think about, let's say, a social network where 2 people are famous and they have so many connections, and there's one person in between them, let's say, that connects, that this person knows both of them, it does sound like, oh, this person only knows 2 people, so maybe that person is not that influential. But hey, that person knows the 2 most influential people in this network, so that person actually is influential. So there's this relationship between your influence is kind of dependent on the influence of your neighbors, and the influence of your neighbors depend on their neighbors, and so on and so on. So this idea of global understanding of the graph, PageRank really illustrates that type of centrality really well. And so here, you're going to see the top 10 packages from a long time ago, up until today, you might start to see some patterns. Some interesting patterns will start to show up more and more. For instance, Compat was pretty strong, had a pretty high page rank for a very long time. And you'll see when, any guesses when that will drop? 2018. Why? Yes? Yeah, you'll see that happen in just a little bit. See, it's starting, the other two are starting to kind of creep up, and Compat will soon start to kind of fade away. And then statistics seems to be a top value, a top page rank value for some time. And so yeah, it's quite interesting to kind of see how things come and go over time. You know, like Compat was there and was the highest page rank value by a very clear differential, but then eventually, because things changed in the ecosystem, Compat started to have a lower and lower influence in the graph. The colors I just left, so I wanted to identify 3 things that like you could clearly track. And these 3, like everything is purple except the 3 that are highest page rank value most recently. So like if you see here, the highest are, oh, well, I guess no, I didn't do that. I thought I wanted to do that. But anyway, basically it's 3 packages that I was interested in kind of showcasing so that you can easily track them. Yeah.
Something to take away from the fact that dates has the highest page rank now? Like what, you have some intuition, or maybe it's just a random artifact of the algorithm?
Yeah, I honestly don't necessarily have a strong sense of why dates is like that. I'll show betweenness centrality in a bit, and that result is way more like evident, and it makes a lot of sense. But for dates, I couldn't, like, I don't know. If anyone has actually hypotheses, I would love to hear it. Like, I personally couldn't think of something why dates has such a high page rank.
So I was going to suggest, I was going to suggest that it would be great to run this and remove the STD list from.
That's fair. Yes. Yeah.
Are test dependencies included? Did you mix them in, or are they excluded?
Test dependencies. I can't remember. There is a way to exclude them, but I think actually it has everything. This data has everything. Yeah. Does that relate to a hypothesis you were trying to?
If you just look at depths, it's not the test dependencies. So you would have to look at extras to actually include the test dependencies.
I see. Okay, then
If you
maybe
don't look at extras,
it's,
then it's not including.
yeah, then it's probably just depths. Yeah. Okay. Yes. Yeah. Yeah. Okay, I will move on to the next. This is just kind of to show you the most recent 2025, May 2025 results. Betweenness centrality, basically we're running the same exact experiment, except that now we're trying to get betweenness centrality on this graph over time. And the way I would like to usually describe betweenness centrality, well, actually it's pretty straightforward. I can just read this part. The higher the betweenness centrality value, the more the package is on shortest path connecting other packages. And the reason I just said you'll see how the result makes sense in a bit is because I think there's a group of packages where so many packages depend on them, and at the same time, this group of packages depend on so many other packages. So they are kind of like the in-between of paths between point A and point B. And in a bit, I don't want to, actually, any guesses what collection of packages we'll have? Well, it's already showing up. But the plotting packages actually have the highest betweenness centrality scores. Plots already showed up, GR is there, and then you'll see Maki kind of make an entrance here. And yeah, eventually you'll see that the 3 of them will have the highest betweenness centrality scores. Yeah, go ahead, Viral.
I'm assuming this is undirected.
This is directed, actually.
Oh.
Yeah.
And yet plots is on the shortest path.
Yeah.
It's depending on plotting packages, I guess, like meta plotting packages.
Yeah, there's actually many packages depending on plotting packages. It's kind of surprising. Yeah.
We don't have conditional dependencies don't exist yet. So if you want your package to make a plot, it has to depend on plots.
Yeah.
Until way late, right? Yeah, thank God.
And also plots has a legacy, right? Like a lot of people started using plots early on and like it's in their, like if even they wanted to visualize just one tiny result, they needed plots in their package, and then that's depending on it, and then probably they didn't bother change it because it's maybe a simple thing they wanted to show. So, yeah. And then just also for reference, this is the most recent, well, the data is up until 2025, sorry, May 2025. So May 2025's result for between the centrality plots, GR and Mach-E are the top three. All right, triangles, cycles. This was just kind of, I wanted to circle back to this idea of matrices and graphs. What's an easy way to identify if a graph has cycles in it? This is a really easy way. So you have, in this case, you have a very simple graph. You have 3 nodes, 1, 2, and 3. And you can represent this matrix as an adjacency matrix, 3 by 3 adjacency matrix. Row 1 is node 1. It only points to node 2. Node 2 only points to node 3. And node 3 only points to node 1. So this is very 3 by 3 simple graph. What happens if I multiply m by m? When I multiply m by m, I'm basically asking the question how many, basically any ij index here will mean that I have a path of length 2 between I and j. So m times m in this case, this number is now 1, which is saying node number 1 is pointing to node number 3. And that's right, because I can go from node number 1 by 1 edge, a second edge, and I can reach 3. So by just 2 edges, I can reach 3. Now, by 3 edges, I can reach 1. And that's a very straightforward way to understand whether there's a cycle of length 3 in the graph or not. I just multiply the adjacency matrix 3 times. And then if I find any entry, oh, this is the wrong matrix, sorry. This should be all ones on the diagonal. Then if I find any entry, like fixing it should be easy, so I'm bothered by it. Sorry?
You want 10 cubes.
That's right, thank you. Yeah, okay. Here we go. So m times m times m is going to be this diagonal matrix, which basically is saying, okay, well, I can reach 1, 2 to 3 by 3 steps, back to 1, that's 3 steps. So the good news is that there are no cycles, which I hope that is something we would expect. So yeah, no cycles in the package dependency graph. Okay.
If you would actually find someone, that would be funny.
Yeah.
I have a question about that.
Yeah.
So you're talking about this as though it's packages depending on each other, but that's not really what happens. It's versions of packages. Versions depend on packages, and then packages have versions. So have you thought about how to represent that as a matrix? Or?
Yeah, that's a great question. It is very complicated. Yeah, we tried to have Claude actually help with that, and that did not go anywhere. Yeah, we tried, like, yeah, it's, I think this project kind of started as like, oh, let's just get the dependency graph, like, fun little thing. And then like one thing after another, it's just like we're finding out all these problematic, kind of more complicated corner cases. Yeah, I don't have a solution to it, but I think that's a really good path to grow this data. Okay, clustering coefficients. So just kind of a quick idea about what clustering coefficients are. Clustering coefficients kind of say, if I have a high clustering coefficient, that means that my neighbors around me have a high likelihood to cluster together. And what that means in the package world, it means that basically if I'm part of a like if I am a package, I end up depending on, like, I basically have another package in my project, and we kind of like, we end up forming a clique. We end up forming kind of a cluster together. And I'm imagining there are types, well, you'll see some of the data, some of the packages do, there's a lot of packages that kind of depend on each other a lot. But the good news is that there isn't a ton of them. So it's not like our package ecosystem is like, oh, there's a package group here, package group here, package group here. There's a bit more. If it was very heavily clustered, that's kind of like not like that. That is, I wouldn't say that's a great signal. And just to kind of clarify what this plot you're seeing on the screen here is, Basically, clustering coefficients in the directed case, you can think of triangles as two ways, well, multiple ways actually, but the two that I chose here is the in triangles and out triangles. So in this case, I'm trying to find the clustering coefficient of this node, and I'm saying, okay, there's two packages that are depending on me, and then one of them is depending on the other, whether in this direction or that direction. And most packages had a 0 clustering coefficient value. Even, like when I ran it on this data set that is the most recent May 2025 one, there was roughly 1,600 of them, or a little more. 1,600 out of 12,800, that's like not a crazy number. But it's also interesting to see how the non-zero values have grown over time. So most recently, there's only about 1,600 packages that have a clustering coefficient higher than 0. And even early on, there wasn't a lot of them. So that's one scenario. But you'll see, okay, and then this is just kind of some results, but I'll skip this part. You'll see the out triangles counterpart has a lot more of this pattern, where basically the clustering coefficient here is I am a package, I'm depending on two things, and then there's a link between them. In that case, there's much more, like 6,000, but still that's not a ridiculously crazy number as well, given that we have about more than 12,000 packages. But that's just a way to understand that, okay, well, there are some groups of packages in the ecosystem that does kind of end up clustering together, but there's not a crazy amount of them. And this is just the results. And then finally, I did want to talk a little bit about some dependency graph of a given package. So for instance, you can see here, this is, I think, the graphs one, but I can get the Mach-E one, and let's hope this works. It does. And this is actually pretty interesting. So this is Mach-E. And if you look at these packages over here, these are all the JLL packages. Well, JLL wrappers. You'll see they kind of cluster together here. And if I remove, yeah, it's kind of hard to. But basically, there's these two big clusters. I will try and show maybe something. Let me actually try this one. Yeah, they're more tightly connected. Yeah. And these are, I think, the JLL, yeah. And then so this was graphs in 2020. That sounds, oh, okay, sorry. Okay. This, okay, so this is, the other thing that maybe like this type of visualization is helpful for is actually also understanding like over time, if you're starting, how far, for instance, this is graphs.jl, but like how many packages are starting to depend on, that's one number that you are, you can just go and see in your Git repo. But also you might be interested in like how long is your longest dependency, your recursive dependency, for instance. That is something you might want to be careful about if you end up finding one package that is, like you only need it for a tiny little thing, but it's bringing in all these other packages because of some reason. That's just some understanding that you can build about your own package, and in case like you want to go and implement that tiny little feature that you're using from a different package, you might just save time and every time you someone tries to install your package. So just some things that you can think about and kind of understand about your packages as you're building them. And then I have less than 5 minutes left, so I will wrap up. Go back to here. Just some notes and next steps. Snapshots will be, we are going to generate them for every commit. They can be generated daily or at whatever other timestamp people are interested in. a lot more questions to be answered. I really barely scratched the surface here. Full data is, it said now available, but it's not, I guess. I just showed that. But it should be available very soon. And there's also, you can reproduce the data. There's steps to reproduce it in the repo itself, so that should be straightforward. And then the other thing is, time goes on, and maybe this data will be obsolete soon. So the idea is to hopefully try and automate updating this data over time. So yeah, and with that, thank you everyone for your attention. Thank you, Willow, for the organizing the mini. Yeah.
Yeah, we have time for a question or two.
Yeah.
Yes, I was expecting to see references to the graphs or metagraphs packages. Did you use those? And if not, how does your software relate to those?
I used graphs in the building of the building. Like, for instance, between the centrality, that's how I used the graphs package. I used the graphs package to actually do the plotting as well, because it integrates very nicely with GraphMaki. So yeah, a lot of the internals, once you see the code, a lot of these packages are part of the code. Yeah, sorry if I wasn't super clear about that. Yeah.
Any other questions? Okay, we'll set up for our next speaker. Our next speaker is James Fairbanks. James is an assistant professor at University of Florida, previously affiliated with GTRI, the Georgia Tech Research Institute. James is a professor in the mechanical engineering and aerospace, is that right, department?
Yeah, mechanical and aerospace engineer.
Yeah, so I'll have James take it away. One short announcement, Ray, the short announcement is that at 4 p.m. there is a keynote.
Yeah, John Herkel's keynote in 1:20.
In 1:20, and at 6 p.m. there's a poster session for like a JuliaCon poster session, so look out for that. Okay. Take it away, James.
Cool. Great, thanks. So we just talked about using graphs to analyze data, and my talk is focused on going beyond graphs towards things like simplicial, hyper, and relational structures. It came up in a great question by Stefan about the package dependency graph, right? Isn't a graph on packages. It has these extra things, these versions playing a role, right? So I'm motivated here by this idea that whenever we're doing graph analytics, there's always more structure than just the graph. That can be like this version structure and the dates, like in this package dependency modeling. It can also be things like dynamical systems. So you have a multi-agent network, you have a communication graph of what agent can talk to what, but then those agents are doing something physical. So there's always additional structure beyond the graph, and I want to get into that. So Algebraic Julia is a ecosystem of packages, and it has a fairly large team behind it. Here are some headshots of people who've worked on various algebraic Julia packages. I'm currently getting notifications from my students who are watching the live stream. So I don't know how to turn on Do Not Disturb here. Focus? Yeah. I don't need the live commentary from you. I'll leave the student nameless. Okay, so attributes. So attributes are a data model that generalizes graphs. So it stands for attributed C sets. This is a pun on G sets, which are group actions. C sets are category actions. So totally weirdo name, but we like it. And so they are an in-memory implementation of a categorical model of relational databases. And each database schema can often form the backbone of a algebraic Julia package. So some are combinatorial spaces, which represents things like simplicial sets, which are used in topological data analysis and computational physics, or Petri nets. We have a package, algebraic Petri, which does like process modeling for like concurrent processes, and you could use that for verification and validation of distributed processes. So here's an example, and I was talking with some GraphBlaws people here today at lunch, and we're talking about like what do the numbers when you have weighted graphs, what do the weights mean, right? So there's always more structure. Whenever you have a graph, there's always more structure. And so something like a roadmap, right? You think of a roadmap, and if you're a network science person, you might pitch road maps as their graphs. Well, but also the edges have lengths that are the lengths of the road segments. And also the vertices have coordinates, the x and y coordinates. And like, ooh, but the lengths should really correspond to the difference between the points, right? And so now a road network is not a graph, it's a relational database. So you have like an E table. Well, I should first start with the V table. The V table is for vertices. The E table is for edges. Then you have some type that's going to play the role of numbers here. And every edge has a source vertex and a target vertex. Every edge has a length. Every vertex has an x coordinate and a y coordinate, right? And so this is the relational database schema for how to store a road network. I said that, but road networks are actually more complicated. Edges are not, they're not by length, they're like a whole geometric curve, right? So the more you dig into any modeling activity where you're using graphs to model something, the richer the structure you'll find. Cool. And so we have in Algebraic Julia, we have a little DSL for specifying these schemas and then automatically generating all of the Julia types necessary to represent databases over the schema. And so all of that's automated. I think a lot of the reason why people don't do these custom data structures for their problem, and they try to fit everything into a graph or fit everything into a matrix, is like, I don't want to do all the work of implementing a whole graph theory library just to do like my special type of graph. So I'll just do like graphs with arbitrary metadata, and then trying to use them, like, I'll show more examples of this later. It's kind of complicated. So atchets have two perspectives. One is just as data structures. You have a domain-specific language for specifying the schema, and all of the implementation is automatically generated from that specification. It covers anything that's like a graph, so any kind of network science-y type thing. We call them combinatorial structures. They come with efficient indexing and reverse lookup, so that they have a generalization of the adjacency matrix, of the like sparse adjacency matrix that they can use. They have serialization and deserialization all auto-generated for you. And you can convert between them with a package we have called data migrations that lets you do things like take a road network and forget the embedding and the lengths and get a graph, right? So automation, not only automation of the individual implementation, but also automation of the conversion between different schemas is really important to make this work. Then atchets also live in a category. So you don't just have a set of databases over a schema, you have a whole mathematical structure called category, and it has really cool things that let you do things like compare instances. So just like graph homomorphisms let you compare graphs, talk about subgraphs, stuff like that. For every schema, there's a notion of homomorphism between database instances. I'll show you a little bit here. Yeah, so that notion of morphism allows you to imbue every such category with a logic. So you can think of, you have a domain of discourse, which here is a graph, G, and you can pick subobjects. We'll pick two subobjects, A and B. So the blue, the part that's highlighted in blue is the subgraph that this proposition refers to. So A is this part, and then B is this loop, and these guys over here. And then you have logical connectives like and or. So and plays the role of intersection, or plays the role of union. You have things like complements and subtraction, so you can do A minus B. You have negation and double negation. And then you have operations like expansion operators, expansion and contraction. And these logical primitives let you write generalizations of graph algorithms. So for example, the not operator always does the notion of induced subgraph. So if you start with a notion of subgraph, and you want to find the induced subgraph that corresponds to that graph, to like those vertices, you can like double negate. And that will work not just in graphs, but it will work in like road networks, simplicial complexes, hypergraphs. Any combinatorial structure has a notion of an induced subobject, and this logic lets you define that in a schema-independent way. And then the expansion operator lets you define things like breadth first search in a schema-independent way. So it always grows your sub-object by kind of one layer of additional data. Okay. So another example is simplicial sets. Simplicial sets have become very popular for topological data analysis. And simplicial sets are to simplicial complexes the way directed multigraphs are to simple graphs. Right? So they're directed and they allow multiple edges. And so what are they? Well, you have a table of vertices, you have a table of edges, and a table of triangles. This is for a two-dimensional simplicial complex, or simplicial set. Every edge has 2 vertices, every triangle has 3 edges. And then there are things like the simplicial identities down here, which tell you that the edges on a triangle, the 3 edges involved in a triangle, need to form a triangle. So the target of the first edge needs to be the source of the second, and the target of the second needs to be the source so that it makes a triangle, right? So here's the definition of an embedded delta set, and we use these for computational physics, where we need to have them embedded into Euclidean space, and we need them to be oriented so that we can talk about signs, stuff like that. So yeah, once you define this schema, you generate data structures, and they will store these combinatorial structures like this. Okay. Yeah, so why do I care about simplicial complexes? Because we're going to use them in computational physics. And then, of course, they're very popular in TDA, topological data analysis. And this is all based on the idea of the face poset of a graph. So if you start with a graph, you can look at its face poset. So it's vertices and then edges, and each edge has 2 vertices. That generalizes to the simplicial complex, where now you want to store the triangles in this complex, and now your triangles have 3 edges. Right? So this is a thing that extends to arbitrary dimensions. And on top of simplicial complexes, we've implemented something called the discrete exterior calculus, which is a mathematical modeling framework for computational physics that treats the geometry of smooth manifolds as a first-class citizen. So you're not just doing physics in Euclidean space with coordinates. You're thinking directly in a coordinate-free manner about manifolds and physics on manifolds. And then you can think there's a smooth exterior calculus for the continuum, for like Riemannian manifolds, and then there's a discrete exterior calculus, which is algebraically equivalent for simplicial complexes. And based on this discrete exterior calculus implemented on simplicial sets, we have a computational physics language. So here we're using another DSL, also implemented in Julia, to specify a porous convection model. So here we have variables, we have operators, we have equations. This little DSL is describing a computational physics thing. And I wanted to show results. You can't put animations in Beamer. So let me do entire screen. I might regret that decision. So the resulting physics is here in the Decapodes documentation page. This little snippet of code up here. So here's where the physics are being defined. It generates this hypergraph of, this is the computation graph of the physical equations, which again, a rich graph structure with a lot more going on than just vertices and edges. Right? So we have this rich graph structure. Then you make the mesh, which is a simplicial complex, and you can simulate. It uses the SciML simulation stack, so all the time stepping is done by SciML here. Right? And it doesn't really matter what physics that is. It's just cool. Okay. And then I want to put this back into slideshow mode. Okay, cool. So yeah, so these decapodes are they're a system of sparse matrices. Each operator in this, it's actually like a hypergraph of sparse tensors in order to define these physics. Okay, so let's talk about hypergraphs. So hypergraphs are used in numerical computation at the frontiers of things like tensor networks. So you can imagine these being tensors, either like multidimensional arrays, either sparse or dense. And so each bubble is a multidimensional array. Each vertex is an axis of one of those arrays. And what it means for when two systems are connected to the same vertex is that you're going to do a tensor contraction. And thus, this tensor network corresponds to this tensor contraction, where you're summing over these triple products here. In order to implement things like that work with hypergraphs, we actually use a thing called undirected wiring diagrams. These are hypergraphs with boundaries. So you have your subsystems, they interact with variables, and then there's this extra boundary on the outside of the like variables that are exposed to the outer world. And so this undirected wiring diagram framework lets you build hierarchical systems because you can like do a tensor contraction with the result that is a tensor, and then plug that into another tensor contraction, right? And what's cool about this is like, these little diagrams are combinatorial structures. There's a finite number of boxes, a finite number of vertices, a finite number of wires, and so they can be arranged into an hatchet here and stored as a relational database. What I've noticed in the literature is there's a lot of times when people have little variations on a theme, right? They want to do, like my road network example. It's a graph with edge weights and vertex coordinates and stuff like that. And so the PetriNet literature, if you use PetriNets to model concurrent processes, is like all over the place. In PetriNets, everybody's got their own little custom version of PetriNets. And so they have things like species, which are the circles, transitions, which are the boxes, and then input and output arcs connecting them. These are directed multi-hypergraphs, if you want to think about them that way. They're directed multi-hypergraphs. But then you want to like put token, there's something called the token game, which is how you use PetriNets to model concurrent systems. You put tokens on the states, and what the transitions do are they move tokens around, right? So it's like, okay, well, I also have tokens, and every token is in a species or a state. Okay, but like, sometimes the tokens are different colors because they're different kinds of resources. So I have, all my tokens are gonna have colors from some type here. Okay, so now I have colored tokens. And then it's like, okay, I wanna use this as a model of these processes happen at different rates. So every transition is gonna have a rate at which it occurs. So now this would be like a PetriNet with typed tokens and quantitative rates, right? You don't wanna re-implement a whole library around that, because this would require, like, the normal way of doing this, you'd either pick the richest data structure you have, implement that, and then say, well, if you don't want tokens, don't put any tokens in, right? If you don't want rates, set all the rates to 0. If you don't want tokens to have colors, just make them all the same color, right? So you'd either go the most general implementation and find all the other implementations as special cases. Or you'd write 4 pieces of software. You'd write a PetriNet library, a PetriNet with tokens library, a PetriNet with type tokens library, and a PetriNet with type tokens and rates library. Neither of those are good. The people who don't care about token colors don't want to always be setting the token colors the same, and they're going to have bugs and stuff like that because the software is not fit for their purpose. So anyway, this Atchit perspective lets you define the schemas and automatically generate the right data structures. And so that lets you really develop the goal of this whole framework is to let you develop software using the right abstractions so that your data structures are always matched to your application as tightly as possible. And of course, we want to go beyond. Part of the reason linear algebra is so dominant, right? Like it's so useful, and everything goes through matrix, right? Everything goes through matrices. We're Julia programmers. We want to write generic code that is also optimal. So let's do that, right? Okay. Can I get a time check? I saw somebody holding signs up. I have 13 minutes? Okay, I have plenty of time then. Okay, great. So Clique Trees is a new package that's been released and integrated into a variety of other packages. It is for doing tree decompositions, which are a technique for accelerating sparse computations across a wide variety of fields. So I'll talk a little bit about Clique Trees and its performance. So what are tree decompositions? If you start with a graph, you want to decompose it into a collection of subgraphs so that the connectivity information is preserved. And then, like, why do we care about tree decompositions? They show up in algorithms like sparse Cholesky, where the sparsity pattern of the Cholesky factors will depend on a chordal completion of the graph, which is the chordal completion is what you need to compute the tree decomposition, right? So I keep hitting that. So these tree decompositions are deeply connected to how sparsity patterns change in sparse linear algebra. And then they're also used for things like probabilistic inference, tensor contraction, sparse optimization problems. And they're deeply connected to the theory of fixed parameter tractable algorithms. So there's a class of algorithms that your thing is NP complete, so it's intractable in general. But if your input is structured in a specific way, you can build algorithms that are polynomial in the size of the problem, and then all the exponential time is in the structure parameter. So if a graph has low tree width, which means it has a good tree decomposition, then FPT algorithms will be feasible here. Okay. And then, yeah, tree decompositions are not new. They've been known since like sparse Gaussian elimination and sparse Cholesky for a long time. So Clique trees encodes and decodes tree decompositions from vertex orders. So every vertex order induces a tree decomposition. So that's why like matrix reordering techniques, like those from sweet sparse. So matrix reordering and graph partitioning are deeply connected. And it's through this encoding and decoding of tree decompositions as vertex orderings. Yeah, and so clique trees can, given a graph, compute an efficient tree decomposition. In order to do this process, you start with elimination orderings. This is really coming from the sparse Cholesky world, right? What's the right way to reorder my matrix so that when I run Cholesky decomposition, I minimize the fill. So you take anything that can produce a elimination ordering, like approximate minimum degree or METIS can both produce these things, and you start with any elimination ordering, and you can build a tree decomposition from it. So Clique trees has already been integrated with the following libraries, or at least most of these following libraries, for probabilistic inference, Bayes nets, or Scruff, tensor contraction. There's a few options here, and then same with semi-definite programming, combinatorial optimization, and quantum computing. These all rely on fixed parameter tractable algorithms that are using tree decompositions. And so you can schedule a tensor network contraction to minimize the width of the decomposition, which bounds the time complexity. And you want to minimize the separator width, which controls the space complexity. And these are properties of exploiting the tree decomposition. It's exactly like matrix factorization, where you're trying to solve a linear system, you do a sparse LU or a sparse Cholesky to build some to reorder the matrix and build the factorization, and then you use the factorization to solve systems. the corresponding version of that for tensor networks is you first schedule the tensor contraction, and then you have to exploit that schedule. You have to execute that schedule. So time complexity and space complexity are measures of exploiting the schedule. And then here we're going to call running time is what we're going to call the time it takes to compute the schedule, right? So you want to build you want to run the fastest, which means minimizing the width. You want to use the least amount of memory when you execute the schedule. That's the separator width. And you want to have the fastest running time so you can compute the schedules quickly. Okay. And then this has been deployed in existing tensor network algorithms or packages. Okay. And so, yeah, it's integrated with both Ka-Hyper, which is a hypergraph partitioning library, and Metis, which is kind of the gold standard. So these are benchmark plots. The x-axis is our time, the y-axis is their time, and this is the time complexity of executing the contraction. So everything above the line is performance improvement. Everything below the diagonal is performance regression. So we're generally producing higher quality time complexities, generally producing higher quality space complexities. So more of the points are above the diagonal, right? So more than half the time we're winning for space complexity. And then for running time, when we use Ka-Hyper, so the same scheduling, the same vertex reordering backend, right? It's like win 2/3 of the time. When you use Metis, you win 100% of the time. But Metis is faster than Ka-Hyper. So that's to be expected. Yeah. So this, there's a little bit of innovation here in using existing data reduction techniques to pre-process the graph. This is all about shrinking the graph. So there's a couple of different operations you can do. You can exploit something called twin classes. So if two vertices have the same neighborhood, you can treat them as if they're the same vertex. Here the red vertices are being merged and the blue vertices are being merged. And then there are rules here that are like, if you have a vertex that's connected to the graph with only two edges, you can clip this vertex off. And then again, now you find 4, clip it off, 1, clip it off. And these let you reduce the graph dramatically. And Clique Trees alternates these two strategies. It does this twin width, yeah. Oh, that was 5 minutes left. Thank you. Okay, so it does the twin. It finds the twin classes and merges them, and then it applies these rules to clip vertices off. And both of those techniques, by like mixing and matching those techniques and iterating them, you're able to produce very small graphs that you then give to Metis, right? So a lot of this performance is shrinking the input size using these rules, using a state-of-the-art scheduler, and then like reinterpreting what sequence of rules you did to get the right answer. Okay. Yeah, so our high-level conclusions here is that I think whenever we're thinking about sparse data or network science or any application where we're modeling with graphs, we should be open to thinking about higher level structures, right? Either richer structure, where we're including quantitative information and we're seriously modeling. The points are embedded, the edges have length, like really take that stuff seriously. Or richer structures like simplicial complexes and hypergraphs, where you have multi-arity relationships. And then Atchits will help you do that in software. And then Clique Trees will allow you to partition these, like by partitioning graphs, build these tree decompositions. We already have worked out theoretically how to use tree decompositions for arbitrary combinatorial structures. And so that's the future work, is to use Clique Trees on Atchits so that we can build tree decompositions of simplicial complexes or tree decompositions of hypergraphs, or whatever rich data format you have, like Petri nets or whatever you're working on. and that will open the door to parallelism in these combinatorial algorithms. So I think that's on our roadmap, and stay tuned for more development there. Thanks, and I'll take any questions. I'll also show the bonus slides to the stream. Here's how you do semi-definite programming. You rewrite it using chordal decompositions, and that's built into these other libraries. And it's built into JUMP. So the easiest entry point might be using this JUMP module, math opt chordal decompositions. Great.
So are there any questions from the audience?
Yeah.
Do you have any, so this talk is about like abstract composable data structures for stuff like subset scales, complexes.
Mm-hmm.
So are there any built-in methods for like homotopy estimation and things like that?
Yeah.
Repeat your question for the mic.
Oh, yeah. So the question is, like, when you're working with abstract simplicial complexes, are there built-in methods for homotopy stuff? No. The application layer, so the thing we can automate is just like the data structures and like basic manipulation of the data structures. The application layer, like once you have simplicial complexes, you want to compute homotopy or something like that. You still have to write the application. Yeah. For now. Soon you'll be able to ask Claude, can you write me a Julia package for computing homotopy groups of arbitrary abstract simplicial complexes? Yeah.
Have you mentioned knowledge graphs?
Oh, knowledge graphs are awesome. Yeah. So this categorical perspective on databases, there's something called the growth-in deconstruction, which takes an arbitrary relational schema and computes, well, it takes a relational database and computes the knowledge graph that is equivalent. So you can, basically the way it works is it takes your database and it blows it to smithereens by it makes a graph where each vertex came from a row in your database and each edge came from a field in the database. And so this growth-in deconstruction will like explode your database into a knowledge graph, which is a graph with types. Like the vertices have types and the edges have types. And so that is implemented. So if you have knowledge graph, like algorithms for knowledge graphs, you can use them on, like you can integrate them into this framework. Great. Thank you so much.
Let's thank our speaker. All right, the next speaker is me. I'm a little tall. Yeah, so I'll be telling you about a compiler I worked on for sparse array programming. I'm Willow. I'm a postdoc currently at MIT in the compiler group. We work on compilers for tensors mostly and other things too. And I am starting as an assistant professor at Georgia Tech in a week. So I'm really excited about that. Thank you. Yeah, this is my PhD was built on Julia, so I'm kind of proud to be able to say that. I'm wearing my JuliaCon 2018 lanyard when I announced that I would be releasing my sparse tensor compiler soon. Here it is. Here we go. So arrays. I mentioned earlier, like I watch the Slack channel for like every new Julia array package that gets released. We have arrays for everything. Arrays are powerful abstraction, right? They've kind of shaped how we think about like productive programming of collections of data. They're often like the first data structure that we teach. They're one of the first data structures that like ever was, right? Like they had them all the way back in Fortran in like the 50s. So multidimensional arrays have been around. And they're also pretty fast. We get peak performance with dense arrays. Like these dense array frameworks are really like stretching the limits of what the hardware can even do. And we also can get a lot of those benefits automatically. But dense arrays haven't really changed much since 57. So we see arrays that are not dense arrays everywhere. And you kind of even see this in like, the canonical dense array routine. So we have dgem, right? 13 parameters. Obviously, we're not just looking at a single pointer. We need a little more metadata about it, right? Like, is it a transposed array? There's also like these LDA dimensions, right? Which is saying like, if it's a window into another array, we already have views. How big is the stride to get into that window? So this is why we have all these different parameters. And of course, there's other kinds of structures that we see, right? In scientific computing, we have triangular arrays. Don't worry, we got that covered. We have another 7-character name, DTRMM, for multiplication with a triangular matrix. And we can keep going. We have banded matrices, DGBMV, or even symmetric matrices, right? There's a whole, especially the MKL library has a lot of really good, sparse symmetric combinations of implementations. Speaking of sparsity, here we are at the sparse workshop. And so you might have like a mesh. It's really important that we store our sparse matrices using dedicated formats. Because there may be asymptotically fewer non-zeros in the graph than there are entries in the graph. So like this is a critical optimization. But even though we're only storing the non-zeros, we often write our algorithms in terms of the dense matrix. This is kind of the language that we're familiar with, and this is kind of the power of frameworks like GraphBLAS, et cetera, that are describing these operations as bulk operations, even though they're not non-zero centric. And we see, variations in the pattern of sparsity. So like we had a discussion in the keynote today about block sparse matrices in machine learning applications. You sometimes get these in finite element methods. You sometimes get them in quantum chemistry. We also have things that are not sparsity, but they're a lot like sparsity, like run length encoding. So you can store like the color of the pixel together with the number of times it appears. And this is another form of compression that we're doing on the data. And of course, keeping going with image processing, we sometimes see operations represented as structure. So for example, padding, right? Or like if we were going to do convolution. I'm a compiler writer. I don't like supporting I plus j. That's not my favorite thing to do. It kind of breaks all of my edge cases. But one trick that we can do is, instead of representing xi minus j, we can form the tuplets matrix, which is a matrix of circular shifts of the filter. And now convolution becomes matrix multiplication just with like this special structure of matrix. And then the compiler can support it. So structure is challenging for a lot of reasons. Dense tensors, it's really easy because the place where the entry of the matrix is represented is the same as where it's stored in memory. There's like really simple mapping. There's no additional abstractions here. Where what you see is what you get. But with sparse tensors, because we're only storing the non-zeros, it really breaks that abstraction entirely. So we see that here we have our sparse matrix, and here we have a common format. This is the compressed sparse column format. We're column major in Julia. And we see that we're only storing the non-zeros here, the locations that they occur within each column, and then the delineations between columns is the PTR array. And so we need dedicated formats, and we also need dedicated code to operate on these formats. So we can see how this kind of quickly becomes a problem, especially I was talking about all these array packages in Julia. We have a nice array interface in Julia, I think. There's indexing and slicing. We have map, reduce, and multiply. There's also things like broadcast. So we have this like, structural, we have this like fused broadcast interface in Julia. We have transposition, and sometimes, various implementations of einsum packages. You can pick your favorite. And then we have all sorts of different array structures. You have arrays, sparse arrays, padded arrays, fill arrays. I should add a .jl to the end of all of these. Different data formats like CSR or COO. And then, of course, we want to run these on different architectures, right? So we have our coup arrays and our distributed arrays. And getting all of these to work together is a challenge. It's a challenge at the interface level, but it's also a huge challenge at the implementation level, because each combination of these things needs a dedicated implementation to run at speed. And this is a big problem. And I'm a compiler person, so I will tell you that compilers can solve it. And they can. We're going to generate this automatically. This is the argument. So I'll give an example of why sparsity is so challenging. And then I'll show you a little bit about a technique that I've developed that might help solve it. So imagine we're taking the dot product of two vectors. The problem here is iteration. We're going to multiply these vectors by iterating over each of them and summing the pairwise products. So in the dense case, this is pretty easy. We just write the for loop that looks like that. In the sparse case, this gets a little more challenging. So now we have a sparse vector. We're not storing every element in the vector. And the appropriate algorithm to do this is to walk over the sparse matrix and randomly access the dense one. And so we have our little pointer into the sparse matrix, and we have a while loop. When you have two sparse vectors, now it gets tricky. So this is where the trickiness begins. The algorithm to merge two sparse vectors, the canonical one, looks a lot like merging two sorted lists. We'll have a pointer into A, a pointer into B, and we'll increment whichever pointer is behind. And when the pointers line up, that means that they share a non-zero location, and the multiplication will affect the output. And so we go ahead and perform the multiplication in that case. And so I should show the code while I narrate this, but this is what the code looks like. We're figuring out which one's behind with this min operation, and then we do our multiply and increment our pointers. So some sparse inputs even have structure beyond just a list of non-zeros. It's a powerful algorithm that I just showed you. It's called like the two-finger merge, and you might try to adapt it to do other structures. So if we had, say, a row of a banded matrix, and we want to do our dot product with just a regular general sparse vector, we might represent the banded row with singular band with like a start and a stop position, right? Knowing that all of the spaces in between are filled in. And you can use the two-finger merge to do this, but it's going to be like asymptotically less efficient than a dedicated algorithm. So the way that this works out, you end up iterating over every single element in the block, which is like less than ideal. So the way that, this is like the modification of two-finger merge for the block. We can use the structure of this input to do better. So imagine binary searching to the start of the block, and then doing that kind of random access strategy I talked about with the sparse and the dense array. And then you get an algorithm that accesses only the number of non-zeros that it needs to, plus a little binary search overhead. And so this is the more appropriate algorithm to do this. And you see that this is actually specialized to the combination of the inputs. So it's tricky to get this right. So we see, we know how to do dense and sparse pretty well. We add in blocks. Okay, things are getting a little more tricky. We add in all of the other, array.jl implementations. Okay, now we're really in trouble. And you can actually characterize previous compiler efforts on like what part of the space they capture here. Taco's pretty good at dense and sparse. You may have heard of Taco. It's like a sparse compiler. There's also the Halide compiler, which is very good at programming like dense array calculations. There's specialized compilers that do ragged arrays. I take it that ragged arrays show up in machine learning. And of course, we're going to capture the whole space with our compiler that is the last compiler that will ever be written. But the idea is that we need a compositional approach here, right? Like we need to be able to specify what is the structure of the thing in a way that allows the compiler to write code that merges two different structures. And so you can imagine, we have our two structures, a structure over A, structure over B, and we'll represent their structure with an efficient iterator. So you can imagine the efficient iterator over every single element of B would probably involve zero region at the beginning, zero region at the end, and some region, dense region in the middle. I know we don't have yield in Julia, but we're just, bear with me. You can do the same thing for A, right? You know, a run of zeros followed by a singular non-zero and then repeat it a couple times. And we're going to fuse these two iterators within the context of a dense program that we'd like to compute. And then we produce the algorithm. This is the high-level idea of the compiler approach. And so how do we do that merging, that taxonomization of structure? We've implemented a new language called looplets that allows us to describe the little parts of the loop that we're going to use to merge these two things together, the points at which they merge. So the first looplet is the run looplet. It represents a run of a constant value. We also have the lookup looplet, which represents a run, or I guess represents a region of randomly accessible values. It doesn't necessarily need to be memory, but it does need to be randomly accessible. Then we have this spike looplet that we invented, which is a run followed by a singular non-zero. And then, of course, you know, if you have many looplets all in a sequence and they're all the same, then you would join them with a stepper. In the same way that a for loop joins, you know, multiple iterations of its body. Similarly, you know, in the same way that a block of code can join multiple heterogeneous statements, a sequence can join multiple heterogeneous looplets, a constant number of them. And so each of these looplets kind of characterizes the structure of the array that we'd like to implement code for. And so here, you know, at this point, I can emphasize that even though I've represented a spike multiple times in that diagram, there's really only one spike, and it's iterated multiple times in the execution of the code. So there's a little bit of a time dimension there. But we see that looplets can express many different structures. They can express these ragged matrices. You know, you have a lookup followed by a run joined with a sequence. If you have a run length matrix, that's like a stepper over runs, you know, and so on. You can implement many different structures this way. And each one of these structures was previously a separate compiler effort. So the way that we lower looplets, the way that we compile them, is that we'll start at the top of each tree, and we kind of always pop off the top looplet each time. There's a priority of which looplet should really be compiled first. And this hierarchy of looplets gives us a lot of opportunities to do optimizations like sparsity with simpler compiler technology like rewriting. So we see we can implement sparsity literally as like applying a rule of x times 0 equals 0 at some point in the compilation of this program. And of course, we did this with symbolic utils, which is like a strength of the Julia ecosystem that this was waiting to be used for this application. So like to give an example of how this might look, you know, we're compiling our looplets. We have these two sequences. We consider like the superposition of all of the splits. So we're looking at this first region. We're going to lower a run of zeros together with like a truncation of the stepper. And we see, boom, we don't need to lower that. We can prune that subtree because x times 0 equals 0. And so that's how sparsity is implemented in Finch. And the nice thing about this is that you can use this to do many other kinds of simplifications. If you need to simplify an if-else operator or something like that, you could imagine writing your own rewrite rule for it. So I'm going to zoom through some of these slides because I want to get to like a little bit of a demo, maybe. We'll see. So this was sort of the core technological innovation of Finch that allows us to write this compiler. Of course, all I've talked about is single-dimensional iteration, right? There's a lot more in this compiler than just that. So we also, we use those looplets to implement a library of formats, many different formats. And then, you know, we combine that, of course, with our simple loopy code that describes the overall strategy that we're going to use to implement kernels. And that the combination of these things goes into our compiler, and we get our efficient code. So we'll talk a little bit about formats, the way that we implement them with trees. And then we'll talk a little bit about the language. So, of course, we all know the CSC format. We can kind of conceptualize this in Finch by thinking of like nested vectors of vectors. So if you imagine having a dense vector of sparse vectors, and then you merge all of the levels of the tree together, that would give you your CSC matrix. Here I'm doing CSR. This is a different presentation to a row major audience. So we have, so you might notice like this tree's good, but it's not best. Like there's a few empty nodes in this tree. You could get rid of those nodes by turning this dense vector at the top into a sparse vector. So here we have like a sparse vector on the top, and then you have a more efficient tree. This is the so-called doubly compressed CSR. Then, like, if you want, if you have like a weird matrix like this, you could have a sparse vector of dense vectors, and there really isn't a name for this kind of structure, but that's sort of the point, is that this gives you a language with which you can kind of parameterize your data and however it looks, in your application. One thing to note is that, like, under the hood, these are kind of stored contiguously in memory, and that forms, if you're familiar with these sparse matrix formats, it forms the traditional component vectors of like PTR and IDX and val, or et cetera. So we represent all of these with looplets to do the iteration over them. And we have an expanded library of the kind of vectors that you might choose at each level in the tree. So you can do things like a run length vector, or a sparse vector that only has one non-zero, which is like a nice specialization sometimes. Or maybe it's like runs with a background of zeros. We have lots of different combinations. And if you're very motivated, you can add your own. And we represent iteration over all of these with looplets. And you can combine them to form really interesting formats. So one format that is my favorite to point out, even though it's like kind of the null case, is the sparse interval of a sparse interval, which is kind of representing a bounding box, which is sort of cool. It's just two singular intervals in a multidimensional sense. So we've talked a little bit about formats. We can also talk about control flow that Finch uses for its internal loopy IR. We kind of use just regular dense for loops because it's the easiest for the programmer to understand. And of course, these loops get sparsified. So you could imagine, as an example, we're going to do a matrix vector multiply, and then followed by another matrix vector multiply with the same matrix transposed. And you might do this by, you do the first mapmul into this vector t, and then you multiply t by a again, and you get y. And so even though this is kind of represented in a dense way, we can use the Finch compiler to produce a sparse implementation of this. Of course, the eagle-eyed listener will notice that the action of this kernel on T is stationary, and so we really only need like a scalar temporary. And so that would be represented like this, and then we can just fuse those two J loops together. And so that would be a more efficient implementation. And the benefit of this is that you can kind of see the overall structure of the kernel and then specify the format separately. I have a breadth-first search example, which is really interesting, and we're going to not have time for it. So I want to talk about the high-level interface because, at some level, I've given you this interface that is like a little bit more detailed and low-level than I would expect like the average programmer to want to get to know. In Finch, we've done a lot of work to make it easier for the programmer to actually use this system by automating the production of this low-level IR. So, you might imagine that you have your programmer, they're programming some high-level like Python or Julia, they're programming some high-level like Python or Julia, and they don't want to write this like really low-level IR, and so we kind of need to write it automatically. Previously, we had like performance engineers would serve this role. They're like writing schedules or something like that. But if we really want to advertise that our interface is at this high level, we need this to be automatic. So now we need to have like an algorithm to make the kind of asymptotic trade-off decisions that are involved in picking formats and loop orders, things like that, for this sparse code. To give an example of like why this is sometimes counterintuitively hard, consider this kernel. We're going to multiply two dense matrices and then sample it with a sparse matrix pointwise at the end, like this. So you can imagine the straightforward way to do this would be to do the multiplication and then do the pointwise. But if we do that, then we're going to get like this n-cubed kernel. If instead you do it all at once, then you can compute just the dot products from the mapmul that you needed for the output. So here we're saying like do the first row together with the first row, and then the next step would be the first row together with the third column, right? And so that would be the optimization here that we're talking about when we're thinking about which inputs to fuse together and in what order. It's a very similar problem to what James was talking about with like the order of tensor network contraction. So it's tricky with sparse inputs because they depend, like the runtime depends on the pattern, like the sparsity pattern that you see at runtime. So we've built this system kind of inspired by database techniques called Galley. This is joint work with Kyle Deeds from the University of Washington. And Galley takes sort of a database optimization approach to actually make this high-level interface possible. So what it's going to do is it takes the input program, which looks something like this, and it runs it through the logical optimizer, which is the high-level fusion decision step. So then we get a set of kernels that are to be computed at once. And then we move that through a physical optimizer, which then allows us to do the physical plan. And this is where we choose loop orders and formats and stuff like that. And at each step of this process, it's actually guided by a sparsity estimation technique, where it's actually like estimating how many non-zeros are in each of the steps. And we found that the choice of estimation, like statistical estimation that you do for this, actually has a big impact on the performance. So here's variable elimination in the language of linear algebra. But one interesting effect of this is that if you're comparing to something like PyTorch, so Finch isn't parallel yet. We're working on it. But if you compare it to a system like PyTorch, even when it's parallel, this decision making about fusion and loop ordering really matters. So here what we see is we're doing a matrix chain multiplication where C is a lot sparser than A and B. And so choosing the right order on this to do B and C first rather than A and B first is a big deal. So we can see as C gets sparser, it's really outperforming PyTorch. There's also a tricky thing going on. I forget the exact reason for why, even when you do it in the reverse order, we're still faster than PyTorch in some of these really sparse cases. And then, of course, there's also the case where if you sum the entire thing at the end, you can get a huge savings by reducing the dimensionality of the problem a little bit. So this is the point of the talk where I was going to do a short little demo. I think I may skip it. We don't have much time. But I will say, I just wanted to do a little bit of at this point I've written a full compiler in Julia. I want to talk about the joys of writing compilers in Julia a little bit. One thing is that reflection and metaprogramming are really powerful. And it's actually very helpful when you're bringing new students into the project for them to be able to splice Julia code into Julia code, and the semantics of all of the ASTs are the same. It's a huge benefit to writing compilers. Another nice thing is that there's many different avenues that you can use metaprogramming for. We can have macros, we have generated functions, and we also have just regular eval, right? And all of those produce speed of light code, and so there's no penalty to using any of them. And finally, the ecosystem can be a strength if you integrate with the existing interfaces. So one example is a lot of Finch looks a little bit like this, where we have a compiler that actually splats some code into a quoted region, and this can be really helpful when you're writing a compiler here. Here's all of our rewrite rules written in symbolic utils. It's not all of them, but it's the fun ones. Couple challenges of writing compilers in Julia. The compile time of Julia itself can be a challenge. Another challenge is that the AST nodes actually all need to have the same type. So if you have different types for each of your nodes, then you over-specialize to all the combinations of those types. The other thing is we have a very fancy system for handling world age and generated functions. I'm glad that Nathan is in the audience because I actually used one of those core.applypure hacks from I forget which commit it was, but to make this whole system work. Yeah, I think at this point I'm going to stop and take questions. Yeah.
Check. Okay. Awesome talk.
I know we've spoken about this a little bit in the past, but what is the like level of support or like maybe timeline for things like GPU acceleration and like distributed multi-threading, like kind of all of those kind of acceleration techniques and Finch?
Yeah, that's a great question. I think the next talk will get into a little bit of the challenges of writing sparse code on a GPU. It's a challenging problem that, like, I think can be difficult to do by hand. One of the things I have to do as an academic is motivate my work by like what hasn't been done before. And so I'm really focused on implementing a GPU compiler that can handle the intersection of multiple sparse arrays, which I think is less of a focus for a lot of the like hand-coded GPU implementations or a lot of the sparse GPU compilers that exist thus far. So I think the answer to your question is that I have two new students, two new graduate students who are, one of them is very excited to work on this problem, and we'll see what happens.
Awesome, thank you.
Yeah, thanks. Really enjoyed the talk. I also have a bunch of questions, but we'll have to catch you later. My main one you talk a lot about this being a compiler, and you mentioned the ways that the compiled code can exploit the structure of each of the matrices in the multiplication or whatever.
Mm-hmm.
Is the structure of those arrays determined at compile time or runtime? Like if it's run length encoded, does the compiler know how long each run is, and is that required, or is that runtime data?
It's runtime data. So you're giving like the format of how you would store that runtime data later. It's not like out of the question that you might encode some of this stuff at compile time. And I think that there's like research interest in those approaches. But for most cases, we're more focused on like having a good balance between what we compile and what's runtime data.
Yeah, that makes more sense to me too. My next question was going to be how bad is the compile time, but I'm glad you do it at runtime. Cool, thanks.
Anybody else?
So you mentioned meta theory and symbolic utils.
That's right.
As someone who's tried to use meta theory, what do you think about the future of these general, beyond Finch, general symbolic rewriting type stuff in Julia?
I guess like one of the reasons that I ended up using meta theory was there's kind of an edge case in like the design of these tensor compilers where you need to ask, does this interval fit inside of this other interval? And we ask this question all the time, and we ask it about like a bunch of complicated formulas of like the left bound and the right bound, and is this smaller than that? And then you're kind of either you're rewriting Z3, you're calling Z3, or you're doing like something with like an E-graph or something like that. And so this is where I ended up trying it out, and it was amazing to be able to, in the same language, try out an E-graph rewriting technique. I had one of my collaborators actually try to call through z3.jl, which we also got working, and it showed some promising improvements, but we didn't want to take a dependency on like Z3 for the main users. But yeah, so I think like I guess it's sort of not necessarily an answer about the future of the system, but just the benefits of like the interaction between these different systems because they all depend on the same term interface.
Yeah. I need to be able to do integer arithmetic inside my term rewriting.
Yeah.
Is I think a big problem that glad to hear that there are solutions for it.
Alrighty, I think remaining questions we'll probably save for later because we got a Zoom call, right?
Yeah, we're going to do a Zoom call.
Alrighty.
Antoine, can we do a little mic check here?
Yeah, sure.
Okay, I need to plug you in. Can you hear me? That's actually an important question. Can you hear me?
Yeah, I can.
Oh, great. Okay. I'm going to see if I can pin you and then full screen you. And how are we doing with? Okay. Okay.
Okay. So we can just share this.
Yes, so Antoine is a student at EPFL, working with Guillaume Dahl. Antoine, take it away.
What did you say?
Oh, take it away.
Okay, so hi everyone. During the last semester, I've been working with Guillaume as well as a few other people from EPFL on a framework to do graph blast and sparse computation with GPU acceleration. And I'm happy to be here to kind of show how we progressed as well as share some of the learning opportunities that we've had along the way. So to begin with, I'm going to start by introducing graph blast because I'm not sure if everyone here is familiar with this. So graph blast is an IPF specification that aims to define building blocks to express graph algorithm and graph analytics in the language of linear algebra. And it uses the equivalence relationship between a graph and this graph's adjacency matrix. So as a basic example, we can see here that if we have a vector with a one-hot encoding to indicate a single vertex, and we multiply this vector by the graph's adjacency matrix, we get in the output the two vectors that are neighbors of the original, two vertices that are neighbors of the original vertex. So this is an example of how we can find the neighbors of the vertex just doing a sparse matrix vector multiplication. There is in fact a lot more we can do by doing a sparse matrix vector multiplication. For example, if we have a set of vertices indicated by one hot encoding of vector, and we multiply this by the adjacency matrix, we can count the number of paths from our original set to every other vertex in the graph. And the main twist with graph blast is the use of usually defined semirings. Semiring, to make it quick, is a set of two binary operators. The first one, which is the multiplication that we're going to use instead of the original multiplication. So that when you multiply a vector by a matrix, we're going to multiply each element of the vector with an element corresponding in the matrix, and then add them all along the column together. What we want to do is we want to do the same computation exactly, but with the twist that we want to use any binary operator instead of binary multiplication and addition. And this gives us a lot of expressive power. For a second example, if we use the addition operator instead of the multiplication, and then the mean operator instead of the addition, it's complicated, and we do this on a weighted graph, we can see that this is equivalent to finding the shortest path from a given set of vertices to others in the graph. So it's a bit abstract, but the main idea is that we want to be able to do a single operation, which is matrix vector multiplication, but with supplying any binary operator that we want instead of the regular addition and multiplication. This is all we need to perform a very wide variety of operations on the graph. While doing this, we encountered a few challenges. The first one is that we have a very high memory to computation ratio. So for those not familiar with GPUs have very large computing capacity with thousands of parallel threads. However, they all share the same memory, and when working with sparse matrix vector multiplication, every bit, every number that we read from memory in the matrix is only going to be used once in the multiplication. So here you have the regular compressed sparse row format. And when we're doing matrix vector multiplication, we're going to be reading the entire sparse matrix once and using each number to do one multiplication with any operator we want, and then one addition, and that's all. So it's very easy for us to be bottlenecked by the GPU's memory bandwidth. And the second challenge we encountered is that we can have trouble with load balancing. So when using the CSR format, the most basic way to perform the matrix vector multiplication is to assign one thread to each row of the matrix. However, if some rows have significantly more values than others, then we are going to have the GPU spend a lot of time in a single row with a single thread assigned to it, and all the other threads are going to be stalled. And once again, we're not going to be able to use the entirety of the GPU's large computing capacity, and this is not ideal. The third problem that we encountered, that as we're going to see have a very nice solution for, is modularity. So as I've said just before, we need to be able to perform the matrix vector multiplication with any combination of two operators that we want, and there is a few dozen binary operators that are defined in the graph standard, and so even more combination of those. So it's not really feasible to implement customized kernels with low level for each combination of operators. And so we're going to use a bit of trickery here to help us. So, do we have any solutions to these problems? The first two problems can mostly be fixed by the storage format. So the high memory and load balancing, they can be partially resolved by using better storage formats. And one nice thing is that this does not really depend on the GPU architecture, and there has been a lot of research to find better and more optimized storage format for parallel execution. However, the bad news is that all this research has concluded that there is not one single perfect storage format for sparse matrices, and the best format will always depend on the specificities and the topology of the matrix that we're considering. So that's a bit of a shame. For the third problem, we used a very nice package from the Julia GPU ecosystem that is called the, I put a typo here, I'm sorry, which is kernel abstractions.gl, which I'm going to jump right in, so yeah, it was written correctly. So kernel abstractions.gl, as its name indicates, adds a layer of abstraction to GPU kernels. In general, whenever we're working with GPU and GPU kernels, we don't have a lot of modularity. GPU kernels are, in general, not a functional programming language. So it can be hard to have this kind of composability and everything that we would want to make this easy. However, this is provided to us by kernel abstractions here. On the left, you can see that we're able to define our sparse matrix vector multiplication kernel by giving as parameters to functions. The move and add parameters can be any Julia functions that have the appropriate number of parameters. And just like this is all we need basically to implement the sparse matrix vector multiplication according to the graph standard. The magic here happens with just-in-time compilation. So basically, anytime we will multiply a matrix and a vector with a new set of binary operators, kernel abstractions is going to compile a low-level kernel with these two operators basically hardwired inside it. And this is this allows us to write a single high-level kernel with parameters, and kernel abstractions is going to generate every combination of operators that the users would possibly want. This is also used by NVIDIA, partially the QSparse library, with the compilation, but it's, in my opinion, it's not as easy to use as it requires users to manually write the code that they want to use as binary operators in strings, and then compile them manually, and then feed them to the kernel. And here we get a very nice integration with the rest of the Julia ecosystem, where we can just give any function as parameter, and the kernel abstraction that is able to do the rest of the run for us. So finally, I'm going to share a few benchmarks and few results. This is all in very early stage, so it's important to keep it in mind. We compared our sparse matrix vector multiplication against the JuliaSparse library, that's one of the standard library. And we can see that when we are using the compressed sparse row format, we are able to get about 1 order of magnitude faster than the JuliaSparse library. And NVIDIA's Sparse library is another order of magnitude faster. We tried a second storage format that is well known to work better on the GPUs for the memory reasons that I mentioned earlier, which is the SELN storage format, which is the circles on the left. And you can see that this storage format, with our implementation, was able to get performances that were close to compressed sparse flow format. And unfortunately, we weren't able to test against Sparse's SELL format because it's not yet implemented with a GL, so there's no binders. And finally, we tried to do some grad spur search, which is a very common graph analytics algorithm, and we benchmarked it against graph.gl as well as the same grad spur search implemented with linear algebra using sweet sparse graph class. And here we were able to get very promising results. This is tested on the randomly generated graphs. And yeah, we can see that we get not only faster runtime, but also a better scaling as the graph size grows. All right, so I think I'm out of time. Thank you everyone for listening, and happy to take any questions.
Does anyone have any questions for Antoine? I'll like repeat them here if it's, audio is complicated. Go ahead.
One very brief question. Just, are there any insights about how to adapt graph laws for Julia, or like designing a specific interface today?
Antoine, did you hear the question?
No, not entirely.
Okay. The question was, do you have any insights on how you might adapt graph laws for Julia, or the experience of adapting graph laws for Julia throughout your project?
Well, so I don't know what kind of insight you're looking for. I would say the biggest part was to set up the corresponding data structures and stuff like this to, in the correct way, to integrate correctly with all the rest of the Julia ecosystem, with stack parameters and stuff like this. As I showed in this slide right here, the actual computation, it's a bit more complicated than what I'm showing here, but it's overall quite simple. So most of the work was also trying to find better storage format that would work well with most matrices and GPUs, which is why we settled with the ACLN one.
Great. Does anyone have any other questions? I ran a little long on mine, and I'm up next. So if you have any other questions, I think we have time for one more. Okay. Let's thank our speaker. So I think strictly I'm up next. Ben, if you want to go, you want to preempt me, you can, but.
It's up to you.
Okay. We'll stick to the schedule. Cool.
That's a good one.
So the second thing I'll talk about, Ben and I are here to talk about two efforts that we're both a part of, standardization efforts in the sparse community. Ben will be talking about the sparse BLAs, unifying sparse BLAs vendors, and I will talk about the bin sparse format. It's a file format for sparse tensors. This effort goes back a couple years now to the 21 Graph BLAs Forum, where Eric Welch introduced the idea that we should really start coming up with a better format than matrix market for sparse arrays and tensors. And so this is the result of that. So why do we store sparse matrices and tensors? What's the point of this? One reason is to share data with other scientists, right? We might have a standard set of test matrices like the sweet sparse collection, I know Julia has a really great package for working with those matrices called Matrix Depot, I think. You might also want to pass data between frameworks, right? If you have different tools written in different languages, how does the sparse matrix get from one place to another? Oftentimes it's the file system. You might also want to have like an in-memory data format, and that's another reason to use this. Another reason you might do this is to save results to use them later on your own system, right? Like if you're trying to do some sort of checkpointing or serialization, this is another reason we need these file formats. So I think almost, and you could almost call it like a little bit of a rite of passage of like learning about the sparse ecosystem is learning about how matrix market works. And I think many people in here may have written their own matrix market parser at some point in their career. The way it works is it's a text format. You have your description of the overall parameters, and then it's a list of tuples in text format of the matrix. You have coordinates followed by values. There's a couple of reasons that these kind of text-based formats are like not ideal. One is that they're not fast. Another reason that they can be a little bit, and this is like a complicated argument because it actually, sometimes they are inefficient in their storage. Sometimes they're actually more efficient than storing floats, and we can talk a little bit about that. But for the most part, these text-based formats are less efficient, both in runtime and storage costs. Yeah, we talked a little bit, they're big. You use like a whole byte for every digit. It's also expensive to parse. So like even the fastest matrix market parser doesn't even like saturate the memory bandwidth, which is like, we can do better. We're storing a matrix. So one of the reasons this is like, another reason that matrix market is kind of not ideal is that we just talked about all of the different sparse matrix formats that exist in the ecosystem, right? We have the CSR and the COO formats, and we have SELL, right? So matrix market doesn't consider the format. So before you store your matrix, first you need to convert it into COO, and then you can serialize it to text. And this is the state of the art still. Oftentimes because it's slow, people develop their own custom formats, right? We have a couple like one-off implementations of binary storage for sparse matrices. But of course it's not portable, right? Because we kind of need a standard for everybody to be able to be in on it. So if we can have this standard, then everybody is able to, no matter where you are, write your sparse matrix to binary, and then anyone else can read it without you two actually having to communicate. So this is the, ta-da, we implemented bin sparse. Bin sparse stands for binary sparse. And the idea behind it is that there's a JSON header that describes like your sparse format, describes your fill value, what kind of things are you storing, is it symmetric, right? These kinds of things all live in JSON. Describes the size of the matrix or tensor. And then there's going to be one or more dense arrays, right? These constituent sparse array buffers stored in a binary container, something like HDF5, ZAR. It could be NPZ if you're like, old school and you want to work with Python. So like one of the benefits of doing it this way is that we can support many sparse matrix formats. So we can support dense vectors. We also have, hard-coded formats for all of the major sparse array formats, right? Like, row major, DCSR, CSR. We also have a couple structural annotations for like symmetry. And the bin sparse matrix under the hood looks a little bit like this, where we have these named fields of like the pointers and the indices. We also support custom formats in bin sparse. So I was talking a little bit about how we can conceptualize formats as trees. And this is reflected in the bin sparse standard. So the bin sparse standard also includes a couple annotations, and you can build your own tensor or format that fits your use case. So this is how we handle the 4-dimensional cases where maybe the formats are a little less standard. So it's pretty similar to the Taco specification. You have things like, this nested JSON description that has like dense and sparse, and then at the very end you have your like leaf level, which is a bunch of elements. And we've seen this before. So in practice, we have a reference parser in HDF5. It stores the JSON descriptor in the group attribute of the HDF5 object. All of this was really easy to do for, Finch supports bin sparse, and it was easy to do because there was an HDF5.jl, and so it was like pretty straightforward. Many thanks to those who have developed that package. But we store the JSON descriptor in the group attribute of the bin sparse object, and so this is like a lot of these binary containers have this capability to store headers or things like that about the data. And one of the benefits of doing it this way is that we can support multiple matrices in the same HDF5 file by like having different subgroups for each matrix. And then we have a little bit of data showing what I think you could expect, but I mean, still we will show you. It is actually faster than storing it in text, even the fastest matrix market parser known to man. We can be faster using this bin sparse format. So here, this is the MTX. This line on the top is the file size of an uncompressed matrix market file, and then down here we see some of the bin sparse formats for COO and CSR in uncompressed and compressed file sizes. So we see like an average reduction here for these various representations, and if it's just for CSR, then we're seeing like average reduction of about a factor 2, a little bit more. Then we can also talk about like the speed at which this happens. And by the way, this on the x-axis, it's the file size in matrix market, like the original file size before we started all this. Each dot represents a singular matrix from the sweet sparse matrix collection, and this graph has all of the matrices from the sweet sparse matrix collection. Is it missing 1 or 2, or?
With more than 1 million non-zeros.
With more than 1 million non-zeros, so we left all the small ones out of there because we didn't want our header to mess stuff up. But yeah, so I actually you can see that the read times are also improved by a similar factor, maybe a little bit more. We see like an average speed up of 4x in terms of like read and write times for sparse matrices, which is good. And I think with that, I want to leave it up to questions. So you can check out the specification online. I encourage you to contribute if you have thoughts and opinions about sparse matrix file storage. We have, bi-weekly meetings. We're still standardizing a little bit, approaching 1.0. And I want to take questions because I think your feedback is really valuable. So I'll stop there. Yeah, go ahead.
Why gzip rather than like LZ4 or Z standard?
We're going to have to, I think we just chose a popular compression technique. Yeah.
So the reason is because gzip is built into HDF5. Oh, sure. Yeah, so the reason is only because gzip is built into HDF5 in pretty much all distributions, whereas it may be different in Julia, but at least from the C perspective, you have to set up your own custom like compression setup for LZ4. So for this experiment, we just wanted to use like the tools that are easy out of the box. But in terms of bin sparse, you can use whatever kind of compression or indeed binary storage you want, right? The main thing we're specifying is basically the JSON and how that corresponds to something in memory, right? And you can use whatever storage you want.
This is a very simple question. What did the matrix do that made that made you worse than matrix market?
Yeah, Ben's going to answer.
So this is a very old couple of I think 3 matrices from the Harwell-Boeing collection, which goes back before Rutherford-Boeing, and those are matrices that contain some real values that are succinctly expressible in text. For example, like we have this in the paper. I think it's like 0.7.
Right.
That's
0.7 is not like rationally expressible as a floating point number.
Yeah, it's not expressible as a float 64, right? And so the minimization process we used is basically we read in the bin sparse or the original matrix market file as a FP64, and then we tried to downcast to a lower precision. And if we had a different result, then we consider this, oh, we have to store it in FP64. So in that case, matrix market is storing 2 bytes, right? And we're storing 64. Yeah. But for most matrices, that's not a problem. Yeah.
Right, those are clearly extremely
Yeah, yeah, yeah. And this is also partly an artifact of like how Tim Davis generates the sweet sparse matrix collection. Yeah, we can talk more about that offline.
I have a question about like coverage of weird matrix formats. So like, I've been in some of the bin sparse meetings here and there, but like, how much of the potentially infinite like Finch formats can you actually store natively, I guess, in bin sparse? What's your sense of that, I guess?
So currently it's combinations of dense and sparse. Some Finch formats are optimized for runtime rather than for storage. So like Finch has variations on like, it's a hash table, it's a tree. These things all look the same when you compress them down into just a sorted list of non-zeros. But I think that the same paradigm could easily store something like a run length encoded array or something like that if you just want to add that particular level format to the standard. The other extension that we're working on is reshaping so that you can support block formats. So we'll have an extension in bin sparse. You can comment on the PR about reshaped sparse matrices to get something like BCSR or like a batched sparse matrix. Okay, I think with that, it's up to Ben to close out the session today.
I have one final question, which is, can you read these files from Julia?
Yes, you can read these files from Julia. You just need to using finch.jl. So that currently we have a finch.jl parser. I imagine if someone feels motivated and inspired, you can implement your own like sparse arrays.jl parser. Yeah, you can also, once you've implemented your bin sparse parser, many languages will be available to you, including C and Python. And so you can pass your matrices to these frameworks as well.
Sweet sparse also has a parser, right? In GraphQL?
Not yet. We're working on it.
Oh, yes.
Right? Okay. Yeah, I think under construction, open to contributions. Yep, cool. All right. Oh, I should introduce Ben, who's been speaking for the past 5 minutes. Ben is a research scientist, right, at Intel Labs. Ben did his PhD at University of Berkeley, University of California, Berkeley. Go ahead. Oh. Yeah, I see.
Let's see.
Ben, you
I want
studied under
extended display.
Yellick, right? Kathy Yellick?
I was co-advised by Kathy Yellick and Aiden Bullich, who is the spec there. There we go. All right, thank you everyone for coming, and thanks Willow for the introduction and the previous talk on bin sparse. Today I'm going to talk about another standardization effort called the sparse blahs. And unfortunately, there's not going to be a lot of Julia in this talk. There is going to be a lot of C++. But Willow and I hope that maybe there can be some, coordination between the sparse blahs community, the Julia community, about what are the right interfaces, and we can see how we can work together to move this forward. But please do feel free to stop me. I have a couple of points in the talk where I'll try to stop and ask questions, but also feel free to interrupt me. So I don't think this needs much motivation for this audience, but I'll just have a couple of slides to talk about why sparse matrices are important. And I think the first reason that sparse matrices are important is if we have sparse data and we want to perform sparse computation over that data, right? This includes things like graph computation, iterative methods, all kinds of traditional applications. But also, of increasing importance is dense models where we want to interact with the world. For example, if we want to have a dense recommendation system, the world is sparse. And so we need to have a way to interact with these sparse features and to convert them into some low-dimensional dense features that we can then interact with, right? So this is embeddings are these things that transform our data from a sparse space to a dense space, and they're a part of all kinds of models, in particular recommendation systems, right, which drive a lot of viral trends like Labubu, for example. And so it's important to develop interfaces and support for these kinds of tools. So in this talk, I'll have three parts. First, I'll talk a little bit about the motivation and the design principles behind the sparse BLAS, why this is important, and what has come before, where this comes from, what has come before. I'll talk a little bit about the interface itself as it exists, and this is a work in progress, so it's continuously evolving. And then I'll talk a little bit about the reference implementation, which we have this interesting design where from day one, we want to start with multiple vendor backends so that we can run on top of existing frameworks. But we also have a test suite so that we can look at functionality, and then a reference implementation that I've been developing along with some of our other collaborators. So the sparse BLAS in this current effort is essentially two things. It is an implementation effort to implement our vision for a sparse interface. And currently this is being implemented in C++, although we'll likely have C bindings as well. And it's also a position paper and a specification that we're working on for how to perform a sparse computation. And I'll comment a little bit more towards the end. This is also a community. We've been having a lot of workshops in Knoxville. If you're interested in getting involved, I'll have links to the Google group so that you can be on the mailing list and get involved. But of course, as you've heard about earlier in this session, this is not the first time that people have standardized tools for dealing with sparse matrices and sparse algorithms. One of the most important pieces of related work that I have worked on before in my career is graph BLAS, which luckily we covered at one of the earlier talks, but graph BLAS provides this API for operating on graphs using the language of linear algebra. And so that corresponds to matrix multiplications and other operations that use arbitrary semirings to execute traditional graph algorithms using all of the tools that we've built over the years for operating on sparse matrices. Now, graph BLAS has made a number of design decisions that allow aggressive optimization. One of which is to have an opaque barrier between what the user has and the user's data and the underlying implementation of the data structure of the graph BLAS matrix and how the operation will be performed, right? So the user essentially provides a series of tuples, and then those tuples are going to be copied into some format that the user does not know, right? And this allows the implementation, and specifically in sweet sparse graph BLAS, the most robust graph BLAS implementation, which is maintained by Tim Davis, there are multiple sparse matrix implementations, even dense matrix implementations that will be used depending on the particular state of the data. And the graph BLAS API allows this to dynamically switch between these different types of containers based on how the data changes over the course of an algorithm. One of the other things about graph BLAS is that it has a large set of very expressive operations, including masking over matrix multiplications, which is very important for graph algorithms when you want to avoid things like loops when you're doing a graph traversal, but also things like extract and select. Now, these two things are strengths when it comes to graph algorithms, right? They allow a large collection of implementations, but at least in the case of sparse BLAS, we felt like these were two weaknesses that we wanted to avoid for the sparse linear algebra case. Number one, because there is an import cost to moving your data into an opaque data structure. Although there are some ways you can get around that, and Tim Davis has worked on that some in Sweet Sparse. Still, we decided to go in a different direction. The second difference is that we wanted to start with basically vendor support based on the existing libraries from day one. So we wanted to avoid introducing operations like mask matrix multiply that don't already have robust support from libraries. One of the other pieces of related work, of course, is a previous sparse BLAS effort that started in the early 2000s that was quite significant, had a significant spec, had some implementations, but failed to get much vendor support. And in our position paper, we kind of outlined two reasons why we felt this might have been the case. One was that it also had an opaque design, where data had to be copied in and out, right? And this means if you want to use a little bit of the API, right, just to perform one operation that you don't have, there is copying cost to moving data in and out, which for sparse operations can be as expensive as doing the operation itself. So that presents a problem. The second case is the area of focus. The original sparse BLAS focused mostly on one sparse operations, right, where one of the operations is sparse and the other two are dense, as well as some vector operations. And those operations, while they can be difficult to implement on certain platforms, at least for the machines of the day, were not the most difficult algorithms people wanted to implement, like sparse times sparse. On GPUs, things get a bit more challenging. But this kind of examination of prior work led us to a few design principles. And the first design principle is that we want it to be easy to use a little bit of sparse BLAS, meaning that the user can have some data, present it to the library to perform one algorithm, and then get the result of that data, understand what the formats are so that they still control that in their application, and get on with their applications. That sparse BLAS could be one piece of a larger workflow. And as a result of that, as we'll talk about, we decided to use views instead of having opaque objects, where the user understands the data structure of the view and is able to control the output of the format of the data. The second, as I previously discussed, is we want to closely match existing vendor libraries. And to that end, we've, from the start, worked to implement sparse BLAS on top of multiple vendor backends. And we've been lucky to have people involved from various hardware vendors, from AMD, Intel, obviously, NVIDIA, ARM, and others, so that we can understand the libraries as they currently exist and how we can offer a interface that works for all the vendors. The second one is to support GPUs, or the third one is to support GPUs, right, which is an important application use case today, and to offer as unified an interface as we can for using GPUs across all the different vendors. And finally, of course, solving what we consider to be the whole problem, right, of SPMM and sparse times dense, but also sparse times sparse problems. And we're also focusing on a few other problems like SDMM that are kind of emerging in machine learning workloads. Okay, I want to pause just for a second before I move on to talking about the interface, if there are any quick questions. All right, I will continue. So I will, for purposes of time, I'll move through this fairly quickly. But just from a C++ perspective, I want to draw a distinction between an object or a container that owns its data and a view. So an object is something that owns data inside of it. When you create one, it will allocate data. And when you move data into a container, generally there is a copying cost associated with that. And when you create a new copy of an object or a container, it's going to copy all of that data over into a new object, right? A view, by comparison, is a lightweight object that refers to data that is owned by someone else. And so as a result, there are limitations on what can be done with view, right? The view by itself cannot dynamically resize itself. But also, a view is trivial to create. There is a constant overhead associated with just creating this wrapper that describes how data is already living in memory, right? And so we decided to use views in sparse BLAs as a way to allow users to plug in their data into the library. So as you can see on the slide, right, we have a CSR view where the user can specify the scalar type of the values of their data, also optionally the index and offset types that are used to refer to data. And they can pass in either pointers to their data or views of their data in a couple of different ways to produce this matrix view and then pass it into sparse BLAS algorithms. And also you can see we're trying to integrate with existing C++ tools like spans and MD spans that already reference dense data. Now when it comes to two sparse operations where the output is sparse, we still try to maintain this transparency. The rationale being that we want the user to be able to control what the output of the data is, because at the end of the day, they need to get the matrix back, understand its format, and then be able to reason about and manipulate that data in the rest of their application. And so the way that algorithms with a sparse output work is that the user essentially has a two-phase operation where first they compute at least the number of, or the size of the output. The user then allocates enough room for that output, and then there is a fill operation that will ensure that the output is in place and accessible. One other thing about views that I want to mention is that we use them to simplify some other operations, like transposing symbolically a matrix and scaling a matrix. So when you create a transposed view, you don't actually physically transpose the matrix, but instead refer to a symbolic transposition of the matrix, which could be a transposed view object, or it could be essentially converting from a CSR into a CSC. So that you have those different transposed views of the same data. Similarly with scaling, we can simply symbolically scale the data and then fuse the data. This is similar to what's already done, except instead of having multiple descriptors that are passed into the algorithm, we attach these to the object. One other thing is that, and one potential issue with views, one compromise, is that we lose opacity. And so the implementation with just a view is restricted in terms of transformations it can make to the data, right? If we have code like this on the slide, where we create a CSR view and then operate on it repeatedly, there's no opportunity to perform format modifying optimizations. So what we've done in the sparse BLAS specification is introduce matrix optimization handles that can live on top of views that are objects themselves and can contain optimization data about the matrices that will need to be reallocated dynamically depending on the particular use case. When it comes to GPUs, we depend on execution policies. So various vendors have C++ libraries for dealing with GPUs. And so each of them can define their own execution policies. These can be implementation defined. In practice, what we end up using is thrust as a common C++ layer, where thrust provides essentially a framework for allocating data that lives on a GPU, and then utilities for moving data back and forth and for launching work on GPUs. Okay. All right, so I want to talk about another C++ detail, which is the complexity that can arise when you have all of these different kinds of inputs. So having different kinds of views that you can pass into algorithms is very useful from a user perspective. But when it comes to implementation, if you use traditional methods of defining a function, like on the screen, right, where you explicitly say, this function takes in a CSR view, this function takes in a scaled view, it leads to a combinatorial blowup, right? Because we need to provide individual implementations for all these combinations of views. And so while we don't explicitly specify that this has to be the case in the specification, the way that we implement this in practice is through something called concepts, where a concept typically defines an interface, more formally a binary predicate on a type that we can evaluate at compile time. And using a concept as part of a function interface says that the parameter or the argument that's passed in must match the concept that is defined for the parameter. So for example, we could have a summable concept which says that this is a type that we have the ability to call plus on, and we could specify that using a collection of Boolean statements about that type, that this particular expression is valid. And then if we try to compile this function and we get an incorrect result, basically that particular implementation of our function will not, in C++ language, will not participate in overload resolution. Basically what that means is we'll get a compiler error that says, hey, the thing you put into this was not summable. And if we have multiple implementations that are available with different kinds of concepts for different parameters, it will automatically pick the right one. And so in sparse BLAS, we have matrix and vector concepts, where essentially we have certain types that are specified to be matrices and certain types that are specified to be vectors. And then we can use those concepts inside of our function definitions, which ends up being very clean. One other thing that we use in the reference implementation that's very useful is something called a requires clause, which can allow additional additional constraints on the function. So for example, we could have a particular implementation of multiply that specifies that A has to be either a CSR matrix or a view on top of a CSR matrix. B has to be dense and C has to be dense. And then we can use that set of constraints combined with some inspectors that we can use to retrieve information about the stack of views for each matrix to get information about what was passed in. And this is a only slightly simplified version of what SPMM looks like for the MKL backend. So essentially, we take in an A matrix, which is sparse. We take in a B matrix, which is dense, and output C matrix, which is also dense. And then we can retrieve, is either of these inputs scaled, and also is anything transposed, and use that to call into the pre-existing libraries. Okay, do we have any questions before I go into the reference implementation? Yeah.
So this is mostly, I think, about the interface, but a lot of this seems very C++ heavy. Is there any thought so far on what a C interface looks like? Like, has the working group looked at that at all yet?
Yeah, so we've talked about a C interface. It would probably basically reflect what's in the C++ interface, but with type erasure, where you have like type erased objects, and you have to do a lot of this logic that we do at compile time in C++ at runtime in C. But I think pretty much all the things we do in C++, you could do in C at runtime, but yeah.
Have you thought about multiple dispatch?
Oh. So by multiple dispatch, you mean like runtime multiple dispatch? Like
compile time multiple dispatch like Julia has.
I'm actually not super familiar. Maybe we should talk about this offline. I'm not super familiar with the way that I have read some papers on this a while back, but I'm not on the top of my head exactly how Julia's multiple dispatch works. So yeah, we should talk about it.
But I think perhaps like another way of framing the question is, how do you envision sparse BLAs interacting with a language that is designed to have a rich hierarchy of types, that is designed to, handle some of these kinds of like view objects and symmetry objects with like, language level dispatching?
Yeah, that's a good question. I'm not sure I have a great answer for you off the top of my head, but I think there are definitely opportunities to interact there. But yeah, we should talk about that more offline.
Because
yeah.
In general, and as I understand it, you basically build expression tree, which then lazily evaluated at the moment when the computation should happen. And there are already several libraries which does that. They don't do it for sparsity in general, in the more generic way, like how you present, but they do it for dense matrices. So have you thought about just extending the existing libraries instead of bringing something new?
Yeah, that's a good question. I think, we haven't thought, I guess Eigen would be the main piece of work in C++ there.
I would guess Blaze, but it's my personal preference. Eigen could be as well. They do similar things.
Yeah, that's a good point. We should talk about that offline. Yeah. Okay, so I'll talk very briefly about the reference implementation. So the reference implementation is built on top of ranges, which are a C++ concept for dealing with sequences of values. So essentially, a range is anything that has a begin and end, and then we can iterate through in some way. And there's a hierarchy of ranges in terms of what they allow us to do. For example, a random access range is a range where we can access any element at random and constant time. And a contiguous range is a range that represents a contiguous block of memory. Inside the range library, there's a collection of tools called range adapters that allow us to build views. For example, a transform view takes in a range and then provides a view on top of it that lazily applies some binary function to that range. For example, we could lazily apply every element in a range by 2. So with all these range adapters, they essentially provide a bunch of tools for creating views on top of existing data. And so we can use these to create range adapters that provide structured ways of iterating over sparse matrices using ranges. So for example, for a CSR matrix, right, we can first basically look at the beginning and end of a particular row inside the column indices arrays and the values arrays based on the row pointers. Then we can construct a subrange that consists of the column indices and the values, and then we can zip those two things together. And this provides a way to iterate over any one of our rows in a functional way. What's convenient about this is that it allows us to create a collection of different customization points or range adapters that work for multiple different data structures. For example, iterating over the rows is something that you could do for a CSR matrix, a DCSR matrix, a dense matrix, and potentially for other matrices if you're willing to have non-constant overhead to build that index of how to iterate over rows. And then we can have a collection of concepts that define for a particular data structure what ways of iterating over that data structure we have. And so inside of the backend, essentially, we use these iteration concepts to constrain implementations, which then operate over the data structures and implement SPMM, SPJAM, all of these different operations. And as new views are added, including views like scaled view or transposed view that preserve the iteration methods of the underlying views they were created on top of, we can take advantage of those types inside of the existing algorithms. And this makes it pretty straightforward to have a reference implementation that has very high coverage by using these higher level tools that abstract the lower level ways of iterating over data. Okay, so in conclusion, please come join us or provide us with your input. I have a couple of QR codes for our Google group and our GitHub repo. We have a couple of high-level principles we've tried to use, and we're interested in interacting with the general sparse community and finding ways that we can interact with Julia and other communities. So thank you very much, and I can take any questions.
So what I missed is the actual computations. So is it like heavily header-based library, and all computations are generated from these templates, etc., or is it actually have BLAS, like dense BLAS? It have a C core, or it's have some core which is precompiled, and then you just call it.
Yeah. So the reference implementation is currently just header only. So it has full coverage. Whatever template types you pass in for the values and indices, for example, they will compile as long as they fulfill the predicates. For the vendor implementations, they are limited to the precompiled core that the vendor supports.
What do you mean by vendor implementations?
So in addition to the reference implementation, we also have vendor implementations. Let's see. Yeah, similar to the one that I showed here, for a number of different hardware vendors. They run on top of 1MKL, KuSparse, other vendor libraries.
But what is the full list?
The full list of vendors?
Yeah.
It's on the repository. I believe it's, let's see, 1MKL, ARMPL, RockSparse, and KuSparse, and AOCL Sparse. That's what we currently support.
All right, so we're pretty much out of time. We have to get to a keynote that's right across the hall that starts in about 5 minutes. So I'm sure there will be plenty of questions for Ben afterwards. But yeah, please go ahead and head to the keynote room if you don't mind.
Thanks, everyone.